This coffee cup. It feels solid, stable, real. You can feel its warmth, its unyielding surface. If you were to tap it, it would make a sharp, definite sound. If you were to drop it, it would shatter into 100 distinct pieces, each one as real and solid as the whole. This is the world you know, the world your senses report to you every second of every day. Welcome to the science for deep sleep. If this kind of calm exploration into the universe helps you unwind, consider liking the video and subscribing to the channel. And wherever you are right now, whether near an ocean, a forest, a city, or somewhere quiet in between, feel free to share where you're watching or listening from. But what if I told you that its solidity is an illusion? A story your mind has evolved to tell itself? That if we could shrink down, smaller than a grain of sand, smaller than a microbe, smaller even than a single particle of light, we would find that this cup, and your own hand holding it, is almost entirely empty space, a quiet, constant dance of probabilities. In the next few minutes, we're going on a journey to the bottom of this cup, to a place where the rules of our world seem to break down and reality itself becomes uncertain. And what we find there might change the way you see everything. The world you know, a comfortable illusion. Let's start with what feels true. In our world, the world of the large, things make sense. If you push something, it moves. If you let go of this cup, gravity pulls it down in a perfectly predictable arc. This is the domain of classical mechanics, a set of rules codified by Isaac Newton centuries ago. It's a world of cause and effect, of certainty. Objects have a definite location, a specific speed, and a clear path through space. This feeling of solid, reliable reality isn't a mistake. It's a phenomenon known as emergence. Think of a high-resolution photograph on a screen. From a distance, it looks like a smooth, continuous image, a face, a landscape. But if you get close enough, you see it for what it is. Millions of individual pixels, each a single, distinct color. The seamless image only emerges when you view it from a scale where the individual components blur together. Our reality is much the same. The solid, predictable world we experience is an emergent property, the result of trillions upon trillions of microscopic events averaging out into a smooth, coherent pattern. Your brain, the incredible processing unit that constructs your reality, has been fine-tuned by millions of years of evolution to perceive this simplified version of the world. It's a survival mechanism. Our ancestors didn't need to know the quantum state of a charging predator. They just needed to know its position and its velocity, and they needed to know them with certainty. Our senses evolved to filter out the noise, to present us with a user-friendly interface for a universe that is, at its core, incomprehensibly complex. But herein lies the quiet and unsettling truth that will guide our journey. That solidity is a scale-dependent illusion. The rules that govern our world are not universal constants. They are local by laws, applicable only in our specific, macroscopic neighborhood. As we shrink, as we change our scale of observation, these reliable laws begin to fray, and then they shatter completely, revealing a foundation that is anything but solid. The journey begins, shrinking down. So, let's begin our descent. Hold the image of that coffee cup in your mind. We're going to use it as our vessel for this journey into the unfamiliar. First, we shrink by a factor of 1,000. The smooth, glossy surface of the cup's glaze transforms. What felt like polished glass now appears as a rugged landscape of microscopic hills and valleys. Imperfections, invisible to the naked eye, become vast canyons and mountain ranges. The world is already losing its smoothness. Let's push further, shrinking by another factor of 1,000. We are now at the scale of a single bacterium. We move through the surface of the glaze, a layer that now feels like a thick, crystalline canopy. Beneath it, we find the true substance of the cup, the ceramic. It's not a uniform block. It's a dense, chaotic lattice of mineral crystals, silica, alumina, feldspar, fused together by heat. It's like flying through an asteroid field made of jagged, interlocking mountains. The concept of a single, solid, thing is already becoming questionable. It's a composite, a collection of other things. But what are these crystals made of? We press on, shrinking 100,000 times more. The colossal mountains of crystal dissolve into a breathtaking, orderly array. We are now at the scale of molecules, hanging in a rigid, vibrating grid. Water molecules, H2O, trapped during the firing process, jiggle with thermal energy. Long, complex chains of silicon dioxide form the structure's backbone, held in place by powerful electromagnetic forces. From this vantage point, the cup is mostly empty space. The molecules are like tiny specks, separated by distances that are, relative to their size, immense. The solidity you feel when you hold the cup is not the result of continuous matter. It is the result of these electromagnetic fields pushing back against the fields in your hand, a force field repelling another force field. You have never truly touched anything in your life. But we can go deeper. These molecules are, themselves, collections of smaller things. Let's pick one, a simple silicon atom. For a long time, we've pictured the atom as a miniature solar system. A dense nucleus at the center, with tiny electron planets orbiting in neat, predictable paths. It's a comfortable image that still makes a certain kind of sense. But what happens when we try to look at one of these electron planets up close? As we zoom in on a single electron, preparing to breach the final barrier between the classical and the quantum world, the image begins to shimmer. The neat, predictable orbit dissolves. The solid little point we were trying to focus on is gone. The quantum abyss, where solidity dissolves. Welcome to the quantum realm. Here, at the bottom of everything, the reassuring rules of our world no longer apply. The first law of this new territory is a declaration of fundamental uncertainty. In 1927, the physicist Werner Heisenberg formulated what we call the uncertainty principle. It states that there are pairs of a particle's properties, like its position and its momentum, that cannot both be known with perfect accuracy at the same time. In our world, if you see a car driving down the street, you can know both where it is and how fast it's going. But at the quantum scale, the very act of observing a property can change it. To pinpoint an electron's exact position, you have to interact with it, perhaps by bouncing a photon of light off it. But that very interaction gives the electron a kick, changing its momentum in an unpredictable way. The more precisely you try to measure its position, the more uncertain its momentum becomes, and vice versa. It's not a limitation of our instruments, it seems to be a fundamental feature of the universe. There is an inherent fuzziness to reality at this scale. So, the image of a tiny solar system is wrong. That electron isn't a tiny ball of matter. It's better described as a wave function or a probability cloud. It doesn't have a definite position at all. Instead, it exists as a smear of potential, a wave of probability spread out around the nucleus. The brighter parts of this cloud represent where the electron is more likely to be found if we were to look for it, but until we do, it has no specific location. It exists in a state of pure potential, a superposition of all its possible positions at once. The atom, therefore, is not a collection of tiny, solid bits. It is a nucleus surrounded by ghostly clouds of probability. The vast majority of what we call an atom is, in fact, truly empty space, governed by these fields of potential. The solidity of your coffee cup is an illusion generated by the statistical behavior of an incomprehensible number of these probability clouds, all buzzing in unison. This brings us to one of the most famous experiments in science, the double-slit experiment. Imagine a barrier with two thin, parallel slits in it. If you fired tiny pellets at it, you'd expect to see two lines on the wall behind, corresponding to the two slits. Simple enough. Now, let's do it with electrons, fired one by one. If electrons are tiny pellets, we should get the same result, 2 lines. But that's not what happens. Instead, we get a complex pattern of many lines, an interference pattern. This is the hallmark of waves. The fact that single electrons, fired one at a time, create this pattern means that each electron is somehow passing through both slits at once, behaving like a wave, and interfering with itself. But here is where reality seems to bend. If you place a detector at the slits to see which one the electron goes through, the interference pattern vanishes. The act of observing the electron's path forces it to make a choice. It behaves like a particle, going through one slit or the other, and the pattern on the screen reverts to 2 simple lines. The measurement itself, depending on the experimental setup, collapses the wave of possibilities into a single, concrete reality. Reality at this level isn't a pre-written script. It's a performance that changes depending on whether there's an audience. The void isn't empty, quantum fluctuations. We've established that the atom is mostly empty space. But what is this empty space? Is it truly nothing? The answer, delivered by the strange marriage of quantum mechanics and relativity, is no. The vacuum is not a void. It is a seething, chaotic cauldron of activity. This is the world of quantum field theory. This view of physics says that the fundamental components of the universe aren't particles, but fields that permeate all of spacetime. What we think of as a particle, like an electron, is just a localized vibration in its corresponding field. According to the uncertainty principle, the energy in any region of space can never be perfectly zero. It must fluctuate. Because of Einstein's equation, E equals mc squared, these energy fluctuations in the vacuum can, for incredibly brief moments, borrow enough energy from the void to create pairs of virtual particles and antiparticles. They flash into existence, exist for an almost unimaginable sliver of time, and then annihilate each other. This quantum foam has measurable effects. The fundamental properties of a particle, like its charge, can appear to change depending on the scale at which you probe it, because this cloud of virtual particles can screen its true value. The rules are not fixed. The empty space inside the atoms of your coffee cup is not empty at all. It is a frantic soup of phantom particles, a constant storm of creation and annihilation. The stability we see is a thin, calm surface on a deep and turbulent ocean of quantum uncertainty. The rules change with scale, asymptotic freedom. The idea that the laws of physics are scale-dependent is a proven aspect of our universe. One of the most powerful examples comes from the force that holds the heart of the atom together, the strong nuclear force. Inside the protons and neutrons of every atom are even more fundamental particles called quarks. For decades, a great mystery was why we never see a quark by itself. The answer lies in a property of the strong force called asymptotic freedom. This discovery was made in 1973 by Gross, Wilczek, and Pulitzer, and it earned them the Nobel Prize in Physics in 2004. It works in a way that is counterintuitive to every other force we experience. With gravity or electromagnetism, the force gets weaker as you pull 2 objects apart. The strong force does the exact opposite. When 2 quarks are extremely close together, the strong force between them is surprisingly weak. They rattle around inside the proton almost as if they were free. This is asymptotic freedom. But if you try to pull them apart, the force between them gets stronger, not weaker, as if they were connected by a cosmic rubber band. Pour enough energy into the system to stretch this rubber band to its breaking point, and the energy you've added converts into mass, E equals mc squared, and creates a brand new pair of quarks. You don't end up with 2 free quarks. You end up with 2 new pairs of bound quarks. It is impossible to isolate one. This is a perfect demonstration of our central theme. At the incredibly small scale within a proton, the rules say that quarks are nearly free. At the slightly larger scale of trying to separate them, the rules change completely. The stability of the protons and neutrons that make up your coffee cup depends on this strange, scale-dependent behavior. The laws of physics are not universal, they are a function of distance. Reality's frame rate, a metaphor for understanding. To try and wrap our heads around this baffling world, let's use an analogy. Think of reality as a movie. What you see on screen appears as smooth, continuous motion. But this is an illusion created by a series of still images, or frames, shown in rapid succession. We can think of the universe as having different frame rates at different scales. At the very bottom, at the so-called Planck scale, is the ultimate refresh rate of the universe. Here, at time intervals of around 10 to the power of minus 43 seconds, reality is a blur of pure quantum weirdness. This corresponds to the Planck frequency of about 10 to the power of 43 flickers per second. At this level, nothing is solid. Everything is a chaotic, overlapping blur of pure potentiality. Now, let's scale up to the level of atoms and molecules. Here, the frame rate has slowed considerably. We're no longer seeing every single flicker. Instead, we're seeing an averaged-out version. Quantum effects are still present. This is the world of probability clouds and wave-particle duality. The frantic, underlying chaos is beginning to smooth out. Finally, we scale all the way up to our world. At this scale, the frame rate is, comparatively, incredibly slow. We are so far removed from the Planck scale flickering that all the quantum weirdness has been completely averaged out. We perceive a perfectly smooth, continuous reality. We see the seamless image, not the frantic pixels that compose it. A single quantum dot, a tiny crystal just a few nanometers in size, blinks erratically. Its behavior is probabilistic, but when you arrange billions of these on a television screen, they work together to produce a stable, coherent image. The macroscopic image emerges from the statistical averaging of billions of unstable quantum events. The reality you inhabit is the stable image. The reality at the bottom of your coffee cup is the single, blinking, probabilistic dot. The observer effect and consciousness. We can no longer avoid the quiet question in the room. If a particle's reality changes when we measure it, what exactly counts as a measurement? This question pushes us from the firm ground of physics into the murky waters of philosophy, and touches upon the mystery of consciousness itself. The most common scientific view, part of the Copenhagen interpretation, is careful with its language. A measurement is any interaction between a microscopic quantum system and a macroscopic classical device. When the fragile quantum system interacts with the large, noisy, classical world, its wave of potential collapses into a single state. Its quantum coherence is lost. A camera, a Geiger counter, or even an air molecule can act as the observer. But this explanation leaves many feeling unsatisfied. Where is the exact line between the quantum and classical worlds? Physicists like John von Neumann and Eugene Wigner pondered a more speculative idea. What if the final collapse of the wave function only happens when the result enters the consciousness of an observer? This is a controversial idea and is not a mainstream view among physicists. But it points toward a profound question. In this view, the universe exists as a sea of possibilities, and the act of conscious observation is what selects one path, making it actual. The physicist John Archibald Wheeler suggested we live in a participatory universe, where we are not just passive spectators of a pre-existing reality, but active participants in creating it. This does not mean you can turn your coffee cup into gold by wishing it. The probabilities are set by the laws of physics, but it does suggest a deep and mysterious link between mind and matter. It suggests that reality might be a dynamic process, a constant dialogue between the potential of the physical world and the actuality brought forth by observation. What we call reality might not be a fixed script, but a collaborative improvisation between consciousness and the quantum field. Why don't we see quantum weirdness? The problem of decoherence. This all leads to the most important question. If the world is built on this foundation, why is our everyday experience so relentlessly classical? Why don't coffee cups hover in a superposition of being on the table and on the floor? The answer is a process called quantum decoherence. It is perhaps the single most important concept for bridging the gap between the quantum and classical worlds. A quantum system, like our lone electron, can only maintain its delicate state of superposition as long as it is isolated. It has to be kept coherent. The moment it interacts with almost anything else, that coherence is lost. The information about its state leaks out into the environment, and the superposition collapses. Now, think about your coffee cup. It is a massive object made of somewhere around 10 to the power of 25 atoms. It is being bombarded by trillions of air molecules every nanosecond. It is bathed in photons of light. It is interacting with the gravitational field of the Earth. Each one of these interactions acts as a tiny measurement, forcing a tiny piece of the cup to have a definite position. And because all the atoms in the cup are linked by chemical bonds, this loss of coherence spreads through the entire object almost instantaneously. For an object as large as a coffee cup, the rate of decoherence is so astronomically fast that it is, for all practical purposes, immediate. The cup is being observed by its environment trillions of times per second. This constant, relentless measurement is what pins it down to a single, classical reality. So, the quantum weirdness never truly goes away. It is always there, lurking beneath the surface. But for any object large enough for us to see, it is suppressed so completely and so quickly that we can never perceive it. The emergence of the classical world from the quantum world is a direct consequence of this constant interaction. The solidity of our world is not fundamental. It is the result of information being lost from a quantum system into its vast surroundings. If this quiet exploration into the fabric of reality helps you see the world a little differently, consider liking the video and subscribing to the channel. And feel free to share in the comments. What concept bent your reality the most? The idea of a probabilistic electron cloud? The empty vacuum that isn't empty? Or the thought that reality itself might depend on you looking at it? Zooming back out, a new perspective. Now, let's pull back. Our journey to the bottom of the coffee cup is over. Let's zoom out, past the ghostly probability clouds of electrons, past the vibrating lattice of atoms, past the crystalline mountains of ceramic, until we are back in our own, familiar world. The image returns to the coffee cup, held steady in the hands. It looks just as solid and real as it did at the beginning. The cup hasn't changed. It is still warm, still solid. But our understanding of it has been altered. We know now what lies beneath that smooth surface. We know that its solidity is an illusion, an emergent property born from the statistical averaging of countless quantum probabilities. We know that its particles are not solid points but waves of potential, flickering in and out of a definite state as they are constantly measured by their environment. We know that the space between its atoms is a seething foam of virtual particles. And we know that the very rules that govern its existence change depending on the scale at which you look. The solid, predictable reality we experience is not the fundamental truth. It is a high-level abstraction, a user interface for beings of our size. The universe does not become classical at large scales. It simply appears classical because the underlying quantum nature is smeared out by decoherence and statistical averaging. The truth, the bedrock of existence, is the fuzzy, probabilistic, and deeply strange world of the quantum. This realization shouldn't make the world feel less real. On the contrary, it should fill us with a quiet sense of awe. It reveals a universe far more intricate and mysterious than our senses could ever lead us to believe. It means that every object, no matter how mundane, is a gateway to a hidden reality. So the next time you hold a coffee cup, or feel the solid ground beneath your feet, take a moment. Appreciate the illusion. Smile at the grand cosmic magic trick. You are holding an object that is simultaneously almost entirely empty space and yet unyieldingly solid. You are touching something whose fundamental nature dissolves into pure probability the closer you look. You are participating in a universe that exists as a shimmering cloud of potential, crystallizing into the world you know through the very act of interaction. You are not just an observer of reality. You are part of the process that makes it so. And in that connection, in that deep entanglement between the observer and the observed, lies the deepest and most beautiful secret of the cosmos. The world feels real because, at our scale, it works. But the real wonder is in knowing that just beneath the surface is a universe of pure, unadulterated magic, waiting patiently for understanding to catch up. Science just proved your world is an illusion. There is a quiet certainty to the world around us. A sense of permanence in the objects we hold, the ground beneath our feet, and the walls that surround us. Consider the feeling of your hand resting on a surface, a table, a book, your own phone. It feels solid. It feels real. We trust this feeling. It is perhaps the most fundamental part of our experience. We are here, and the world is a tangible, predictable place we can interact with. Our lives are built upon this foundation. The ground supports our weight. The chair holds us. This is our reality, a steady stream of reliable information from our senses. But what if that feeling of touch has never been what it seems? In fact, what if you have never truly touched anything in your entire life? Not another person, not the ground you walk on, not even the body you inhabit. The world you think you know, the solid, stable reality we trust, may be a convincing illusion. This is not a philosophical metaphor. It is a conclusion suggested by the most carefully tested theories in all of science. It suggests the physical world is not quite physical, that solidity is a matter of perspective. And the truth of it is stranger, more subtle, and perhaps more beautiful than we often imagine. The physics is here to help us understand it. If you press your hand against something, you feel a firm resistance. That sensation is a story, told to you by your brain. It is a story of contact, of your atoms meeting the atoms of that surface. But they are not meeting. They cannot. There is a microscopic distance between your hand and that object, a space filled with invisible forces interacting with one another. What you feel is not contact. It is repulsion. You are not sitting on your chair. You are hovering an infinitesimal distance above it, suspended by a field of energy. This is not a fringe idea. It is part of the bedrock of modern physics, the same science that allows the device you're watching this on to function. And it reveals something remarkable. Our senses seem to give us a summary of reality, a simplified version of it. They hide the raw, complex, and almost incomprehensibly detailed code of the universe. Today, we will explore that summary. We will take a journey from the world we think we know into the world that physics describes. We will move through the layers of illusion, from the feeling of solidity to the quantum realm where the rules of reality are written. By the end, you may not just see the world differently. You may understand that you are not simply a thing in the world, but a process, a pattern, a quiet wave of existence in an ocean of energy. The quiet illusion of solidity and touch. Let's begin with the most fundamental illusion, solidity. We perceive the world as being full of dense, solid objects. A block of iron, a wooden table, a granite countertop, they are the definition of substantial. But this is a trick of scale. If you could look closer, with a microscope powerful enough to see the atoms of that granite, you would not find a solid, continuous substance. You would find mostly empty space. Quiet, echoing voids. Atoms, the building blocks of matter, are themselves mostly empty space. A common way to visualize this is the stadium analogy. If an atom were the size of a large sports stadium, its nucleus, containing nearly all of its mass, would be like a single grain of sand on the center of the field. The electrons, which give the atom its volume, are not specks of dust, but more like clouds of probability, existing in the vast space of the upper balconies. The rest is simply emptiness. The chair you're sitting on, the walls around you, your own body, it is all structured emptiness. The solidity we feel is an illusion, generated by interactions happening within that void. So if we are made of mostly empty space, and we're trying to touch an object that is also mostly empty space, why don't our hands just pass through each other? Why does the world feel solid? The answer lies in one of the universe's fundamental forces, the electromagnetic force. The surface of an atom is not a hard shell. It is a cloud of negatively charged electrons. And as you may remember from playing with magnets, like charges repel. When the electron cloud of the atoms in your hand approaches the electron cloud of the atoms in a table, they push against each other with an immense force. This electromagnetic repulsion creates an invisible, untouchable barrier. It is a force field that your nerves detect and your brain interprets as the sensation of touch. But there is no contact. No matter how hard you press, the atoms of your hand and the atoms of the table remain separated by a void, repelling each other through the exchange of particles called photons. It is similar to trying to push the north poles of two powerful magnets together. You can feel the resistance growing stronger as they get closer, but they never truly touch. There is always a gap, a cushion of force between them. This is what happens every time you touch something. You are not feeling the object itself. You're feeling the electromagnetic force that prevents contact. You are, in a very real sense, floating on a sea of energy. Our entire experience of the physical world is shaped by this subtle truth. A handshake is not the meeting of two hands, it's the repulsion between two force fields. A hug is a microscopic gap between two people, bridged only by the interaction of their atomic energy. We have lived our whole lives in a world where nothing truly makes contact with anything else. Solidity is not a property of matter itself. It is a sensation created by invisible forces acting across empty space. And once you understand this, a quiet question arises. If something as basic as touch is an illusion, a story our brain tells us about force fields, what else is our mind translating for us? What other parts of our reality are just a useful summary of a deeper, stranger truth? If this kind of calm exploration into the world around us helps you unwind, consider liking the video and subscribing to the channel. We are just getting started. The path to understanding goes much, much deeper. We're about to explore not just what you touch, but what you see, what you hear, and even your experience of time itself. A world translated, color, sound, and time. The illusion of touch is just the first step in understanding our perceived reality. Now, let's consider color. You look at a ripe strawberry and see a vibrant red. You look at the sky and perceive a deep blue. But that color does not exist out there in the world. Red is not a property of the strawberry. Blue is not an intrinsic quality of the sky. Color is an interpretation created by your brain. What we call light is a spectrum of electromagnetic radiation, waves of energy vibrating at different frequencies. When sunlight hits a strawberry, its surface absorbs most of those frequencies. It reflects, however, a specific frequency, a wavelength of about 650 nanometers. Those waves travel into your eye, strike your retina, and specialized cone cells send an electrical signal to your brain. Only then, inside the quiet, dark theater of your skull, does your brain create the asterisk experience of red. The strawberry itself is colorless. It simply has a texture that is good at reflecting a certain kind of energy. The same is true for every color you see. They are all interpretations, a code your brain uses to differentiate the energies of the world. Different species have evolved to interpret these energies differently. Bees can see ultraviolet light, a color invisible to us. Snakes can perceive infrared, seeing the world as a map of heat. Each of us is experiencing our own unique, biologically tuned version of reality. Reality itself is a colorless, soundless, vibrating sea of quantum fields. The same principle applies to sound. The melody of a violin is not floating in the air. The violin string vibrates, creating pressure waves in the molecules of the air. These waves travel to your ear, causing your eardrum to vibrate. Tiny bones transfer this vibration to a fluid-filled chamber lined with microscopic hairs. The movement of the fluid bends these hairs, which triggers an electrical signal to your brain. And again, only inside your mind is this raw data of pressure waves translated into the rich, emotional experience of music. Out there, in the world, there is no sound. There is only vibration. So, the world you perceive is not solid. It has no color. It has no sound. It is a construction, a beautiful and incredibly useful story told to you by your nervous system. But all of this is subtle compared to perhaps the grandest illusion of them all. The illusion of time. You experience time as a constant, forward-flowing river. The past is gone, the future is yet to come, and we exist in the fleeting moment of now. This feeling is universal and deeply intuitive. But according to many physicists, this, too, might be an emergent property, not a fundamental aspect of reality. At the deepest level of physics, particularly in the equations of general relativity, the distinction between past, present, and future seems to fade. This has led to an idea known as the block universe theory. In this model, all of time, every moment from the beginning to the end, exists simultaneously, like coordinates in a four-dimensional block of spacetime. The flow of time that we feel could be an illusion of our consciousness, like a spotlight moving along a film reel that already exists in its entirety. A newer, and still debated, idea suggests that time itself might emerge from quantum entanglement. In this view, the universe at its most basic level is static. But when quantum systems become entangled, linked in a way that their fates are intertwined, an observer within one system can perceive change relative to the other. That perception of change is time. Time doesn't flow on its own. It emerges from the relationships between things. It is a fascinating idea, a reminder that even our most basic certainties are still being explored. So, our entire reality, a solid, colorful, noisy world flowing through a constant, now, is a fabrication. A mental model. Our senses are not windows onto reality. They are more like paintbrushes, and our consciousness is the canvas. The real universe is a dark, silent, timeless, and formless realm of pure potential and vibrating quantum fields. But if that is the true reality, then how does this rich, stable, predictable world that we live in arise from it? The answer lies in one of the most important concepts in all of science: emergence. The architecture of illusion, emergence, and the power of averages. This is the heart of the mystery. If the microscopic world is a chaotic, probabilistic place, why is our macroscopic world so stable and predictable? Why does a coffee mug stay a coffee mug? The answer is the law of large numbers. The reliable world we know is an asterisk emergent property asterisk, born from the statistical averaging of an unimaginable amount of quantum chaos. The macroscopic world is the one we see, anything from a grain of sand to a galaxy. Here, the laws of classical physics work beautifully. Things are solid, they have definite locations, and their behavior is predictable. The microscopic world is the realm of atoms and electrons. Here, the laws of quantum mechanics rule. Nothing is certain. A particle is more like a probability cloud than a tiny dot. It is a world of pure chance. So how does the orderly macro world emerge from the disorderly micro world? Through the quiet magic of averaging. Think about the temperature of the air in your room. At the microscopic level, what we call heat is the kinetic energy of individual air molecules, trillions of them, all moving randomly. If you could track a single molecule, its energy would be fluctuating wildly. It's pandemonium, but you don't feel that chaos. You feel a steady, uniform temperature. That's because the temperature you feel is the average kinetic energy of all the trillions of molecules combined. The frantic, random movements cancel each other out on a large scale. The statistical average of all that chaos becomes a simple, stable property, temperature. The same is true for pressure. You don't feel individual air molecules hitting your skin. Instead, the impacts of countless particles per second average out into a smooth, constant force we call air pressure. These concepts are the foundation of thermodynamics, a branch of physics that describes the behavior of large systems by focusing only on their statistical averages. This principle of emergence is everywhere. A single molecule of H2O is not wet. But put enough of them together, and the property of wetness emerges from their collective interactions. A traffic jam is not a property of any single car. It's a pattern that arises from the collective behavior of many cars. Our reality is the ultimate emergent property. An orchestra is another useful analogy. If you listen to a single musician practicing, it might sound disjointed. But when 100 musicians play together, following a set of rules, a coherent, beautiful symphony emerges. Our reality is the symphony. The predictable world is an emergent property, born from a chaotic quantum realm we can never directly experience. The apple on the table looks perfectly smooth, solid, and red. But that is just the macroscopic average. Zoom in, and you find a chaotic landscape of molecules. Zoom in further, and you find atoms that are mostly empty space. Zoom in further still, and you find a swirling vortex of probability waves. The apple you see is a statistical ghost. It's a stable pattern, a collective behavior of trillions of chaotic parts that, when averaged together, create the illusion of a simple, solid object. Your senses are only showing you a useful summary of the truth. This understanding changes things. It means the world is not a collection of things, but a collection of processes. An apple isn't a static object, it's a verb. It's a vastly complex process of quantum interactions that maintains a stable pattern over time. And so are you. If the idea that you are a statistical average of quantum chaos has given you a new way to see the world, consider hitting that like button. It tells the algorithm that exploring the fundamental nature of reality is something worth sharing. And it helps us continue to make content that quietly challenges the world as we know it. The observer and the creation of reality. We've established that the solid, classical world is a statistical illusion emerging from a quantum substrate. But there's one more layer to this mystery, one so profound that it troubled even the greatest minds of physics. It is a concept that seems to blur the line between the physical world and our observation of it. It's often called the observer effect. In the quantum realm, particles do not have definite properties until they are measured. Before observation, an electron exists in a superposition, a cloud of all possible locations at once. But the moment you perform a measurement, the moment you observe it, this cloud of possibilities collapses into a single, definite reality. The particle instantly has a location. The very act of looking at it seems to force it to make a choice. This is shown in the famous double-slit experiment. When you fire electrons at a screen with two slits, if you don't watch which slit they go through, they behave like waves, creating an interference pattern. But if you place a detector at the slits to observe which one they pass through, the pattern vanishes. The act of observation changes the outcome. It changes reality itself. For decades, physicists have debated what this means. What constitutes an observer? Does it have to be a conscious human? Most physicists today would argue that any interaction with the surrounding environment, a photon bouncing off it, a collision with an air molecule, is enough to cause this collapse. But the early pioneers of quantum mechanics, like Niels Bohr and Werner Heisenberg, were led to a more radical suggestion that reality is not fully defined until it is measured. This led to a profound philosophical question, one that still echoes today. Does consciousness itself play a role? The legendary physicist John Wheeler even proposed we might live in a participatory universe, one where the act of observation is an active part of creation. Recent experiments have explored this strangeness further. A 2019 experiment looking at a thought problem called Wigner's Friend showed that, under specific quantum conditions, two different observers could witness contradictory outcomes, with both of their observations being correct from their own perspective. This does not mean you can wish a gold bar into existence. The rules are constrained by physics and the powerful statistics of emergence. But it does suggest a deep and subtle connection between the observer and the observed, a connection classical science has long overlooked. This brings us to our final and most profound destination. If the world is an illusion, if we are emergent patterns of energy, and if observation helps shape reality, then what does that make us? What are you? The new reality. We began this journey by questioning the simple act of touch. We have traveled from the illusion of solidity to the emergent nature of our world, and finally to the quiet role of the observer in shaping reality. We have looked at our world piece by piece. So what are we left with? You are not what you think you are. You are not a solid, static being, a thing separate from the world around you. You are a process. You are a stable, self-sustaining pattern of energy and information that has emerged from the quantum chaos. You are a wave in a universal ocean, a temporary whirlpool of complexity in a cosmic stream. You are a symphony of trillions of chaotic quantum interactions that have, through the miracle of emergence, achieved self-awareness. The illusion of a solid world is not a flaw, it is a feature. It is the summary evolution has given us to navigate a universe that is, at its core, incomprehensibly complex. Your senses do not lie to you. They tell you a simplified story, a useful abstraction that allows you to function. They translate the raw data of quantum fields and probability waves into a world of solid objects, beautiful colors, and meaningful sounds. It's a story that allows for love, for art, for science, for the experience of being human. So, the next time you look at your hand, you might see it for what it truly is: a shimmering field of energy. A collection of stardust, organized into a pattern complex enough to ponder its own existence. You can feel the 99.9% empty space held together by invisible forces. You can feel the repulsive energy as you press it against a table, and remember that you are experiencing the fundamental forces of the universe firsthand. You are not a ghost in a machine. You are the machine, and the machine is made of ghosts. You are a temporary, beautiful disturbance in the fields that make up reality. You are the universe experiencing itself. The world is not less real because it is an illusion, it is infinitely more magical. It is a dance of forces in empty space, a statistical miracle, a story being told by consciousness. And you are not just a part of that story. You are its author. CERN just found a glitch in our reality. What if the world we live in, this solid, predictable, cause and effect reality, is just a paper-thin surface, and something is starting to poke through from the other side? You might have seen the whispers online, the dramatic headlines about a late-night simulation at CERN that supposedly found a persistent anomaly, a glitch, in the very fabric of space-time that has physicists stumped. Now, before we get carried away, let's be crystal clear. The story about a 3 a.m. quantum simulation accidentally revealing a hidden layer of reality? It's great science fiction, but it's not a documented fact. There has been no official announcement from CERN about finding a literal glitch in space-time. But there's a reason these stories catch fire. It's because they hint at a truth that's far stranger than any fiction, and that truth is what we're going to explore. The real glitch isn't some bug in a computer program. It's a fundamental crack in how we understand existence itself. It's a chasm that has been sitting in the middle of physics for over 100 years, separating the world we see from the world that truly is. This is the story of how scientists are wrestling with a hidden layer of reality that runs on probability, not certainty. We're going to explore the real puzzles that inspire these fantastic stories, and by the end, you'll see why it forces us to question everything about our universe, our consciousness, and what it even means to be real. The two realities, clockwork and chaos. To get what this glitch is all about, you have to realize that we're all living in two different worlds at the same time. The first one is the world you know. It's the world of solid objects, predictable results, and rules that don't bend. Think of a billiard ball rolling across the table. You can calculate its path, its speed, and the exact angle it needs to hit another ball into the pocket. Every action has an equal and opposite reaction. This is the universe as a giant, ticking clockwork machine. A deterministic reality. This idea of determinism is baked into our intuition. It says that if you could know the exact position and momentum of every particle in the universe at this very moment, you could calculate the entire future and reconstruct the entire past. The future would be just as fixed as the past is. Drop an apple, it falls. Push a door, it opens. Our brains evolved to handle this big picture world of predictable results, so to us, it feels like the only reality there is. It just feels like common sense. But that comfortable, clockwork world? It's a facade. It's like looking at the surface of a still pond. The top is smooth and orderly. Ripples move in perfect circles. But underneath that calm surface is a hidden world. A churning, chaotic, and totally bizarre place where all the rules of our world are broken. This is the quantum realm, the world of the very, very small. And down there, certainty is a myth. Once you shrink past molecules and atoms, down to the fundamental particles that make up literally everything, electrons, photons, quarks, the clockwork machine falls apart. It's replaced by a world that runs on pure probability and shimmering potential. In this hidden layer, particles aren't like tiny billiard balls. They're more like ghosts. An electron, for example, doesn't have one single location as it orbits an atom. It exists in a superposition, a smear of probabilities, a cloud of potential places it could be. It's here, there, and everywhere it might be, all at once. This is the fundamental split in physics, the true glitch in reality. How can a universe built from these uncertain, probabilistic ghosts possibly create the solid, deterministic world we experience? Why does the world of the big behave so differently from the world of the small? For a century, physicists have tried to patch this crack, to find one unified theory for both the clockwork and the chaos. But the more we learn, the deeper the mystery gets. And the hints we're getting from modern experiments suggest that the quantum weirdness isn't just a quirk of the small scale. It might be the fundamental operating system of reality itself, and our normal world is just an illusion that emerges from it. The core of the glitch, uncertainty and superposition. To really feel the scale of this glitch, we have to stare right into the abyss of quantum mechanics. The best place to start is with the most famous, most mind-bending experiment ever conceived, the double-slit experiment. It's so simple in its design, yet so staggering in what it reveals, that the physicist Richard Feynman said it holds the central mystery of it all. Here's how it works. Picture a wall with two thin, parallel slits in it. On one side, you have a machine that fires tiny particles, like electrons, one at a time. On the other side is a detector screen that lights up where each electron hits. Now, if you close one slit and fire away, you get exactly what you'd expect. A single stripe of hits on the screen behind the open slit. The electrons act like tiny bullets. Same thing if you cover the other slit. No surprises. That's our classical, common sense world. But when you open both slits, something impossible happens. Instead of two single stripes, you get a whole series of stripes, an interference pattern. This is the pattern you get from waves, like in water. When waves pass through two openings, they interfere with each other. Peaks add up, and peaks and troughs cancel out. The pattern on the screen proves that the single electron, traveling all by itself, didn't act like a particle. It acted like a wave. It seems to have gone through both slits at the same time and interfered with itself. Let that sink in for a second. The electron left the gun as one particle and hit the screen as one particle in one spot. But in between, it behaved like a wave of pure potential that explored every possible path, including both slits at once. This is superposition in action. Before it's measured, the electron isn't a thing in a single place. It's a wave function, a mathematical map of all its possibilities. The universe, at its core, isn't dealing in facts. It's dealing in possibilities. But it gets even weirder. The physicists, just as confused as we are, decided to peek. They put a detector next to the slits to see which path the electron really took. And the instant they did that, the moment they observed the electron's path, the interference pattern vanished. The electrons went right back to acting like normal little bullets, making two simple stripes. It's as if the universe knows when it's being watched. The very act of measuring forces the electron to pick one, to collapse its wave of possibilities into a single, concrete reality. This brings us to the second piece of the glitch, the Heisenberg uncertainty principle. Werner Heisenberg figured out that there's a fundamental limit to what we can know about a particle. You can know its position with perfect accuracy, but then its momentum becomes a complete unknown, or vice versa. This isn't because our tools aren't good enough. It's a built-in rule of the universe. You can never nail down both where something is and where it's going at the same time. This isn't just a puzzle. It's a direct attack on the idea of an objective reality that exists without us. If a particle's properties, its path, its location, don't even have a definite state until we measure them, what does it even mean for something to be real? Before quantum mechanics, we thought of ourselves as passive observers looking at a universe that was already there. Now, it seems the observer is an active participant. The act of observation isn't just seeing what is, it's helping to decide what becomes. This measurement problem is maybe the deepest and most unsettling part of the whole theory. What even counts as an observation? Does it need a conscious person in a lab coat? Or can any random interaction, like a stray particle of light bouncing off an electron, be enough to collapse the wave function? This is the fuzzy border where the ghostly quantum world snaps into our solid, classical one. And figuring out that transition is the key to understanding why our reality seems stable at all. Bridging the gap, the puzzle of decoherence. So, we have this massive problem. The building blocks of our world are these spooky, probabilistic quantum things. They exist in a haze of possibilities until a measurement forces them to become real. Yet, look around. You don't see any of that weirdness. Your coffee mug is on the table. It's not in a superposition of being on the table and on the floor. It doesn't randomly tunnel through the wood, even though the electrons inside it have a tiny, non-zero chance of doing exactly that. Why? If everything is made of quantum stuff, why doesn't everything act like quantum stuff? This question stumped physicists for decades. The best answer we have so far, though it's still not the full story, is a process called quantum decoherence. The core idea is simple. Nothing is ever truly alone. That ghostly superposition of a single electron in the experiment is only possible because it's in a super-controlled, isolated bubble. But out here in the real world, things are messy. They're constantly interacting with everything around them. Your coffee mug isn't one quantum object. It's a giant collection of trillions and trillions of atoms. And those atoms are being constantly bombarded by air molecules, light particles, and heat radiation. Every single one of these tiny interactions acts like a tiny measurement. Every time an air molecule bumps into your mug, it learns where the mug is. That information leaks out into the environment at an incredible speed. The quantum coherence, that delicate state where all possibilities exist at once, gets destroyed. The wave function collapses, not because a scientist is looking, but because the environment itself is constantly looking. Think of it this way. A single quantum particle is like a perfectly balanced spinning coin, both heads and tails at once. But a big object like a coffee mug is like trillions of those spinning coins all linked together. The slightest breeze is enough to knock them all over, and they'll all land on the same side, heads or tails. The quantum possibilities get averaged out into one stable, classical result. The weirdness is still there under the hood, but it gets washed out by the sheer noise of the big-scale world. Decoherence explains why we don't see quantum effects in day-to-day life. It's the bridge from the quantum to the classical. It shows how the predictable world of billiard balls and falling apples can emerge from the probabilistic world of ghostly electrons. Reality seems to snap into focus for us because the constant chatter of the environment averages out all the quantum fuzziness, turning probabilities into what we see as solid facts. But decoherence isn't a perfect fix. It's more of a description of what happens than a deep explanation of why. It explains how a system loses its quantum nature, but it doesn't fully solve the measurement problem. It still doesn't tell us why, out of all the possible realities encoded in that initial wave function, we experience this specific one. It explains how we get a classical outcome, but not why we got this one. This is still a huge area of active research. Scientists are running experiments trying to create bigger and bigger objects that can hold onto a quantum superposition, pushing that boundary between the quantum and classical worlds. They're trying to find the exact line in the sand and figure out what a measurement truly is. The answer could be the final key to why the world looks the way it does. The next layer down? Speculative frontiers. The fact that our solid reality bubbles up from a fuzzy quantum soup is already a lot to handle. But this is where the story gets really wild, touching on the kinds of ideas that fuel those sci-fi stories about CERN. While a single experiment finding a crack in reality is fiction, the theories that physicists are exploring to get past our current models are just as crazy. They're asking a radical question: is spacetime itself fundamental? Or is it, just like the solidness of your mug, an emergent property of something even deeper? This brings us to a mind-bending and very theoretical idea: that spacetime isn't a smooth, continuous sheet, but a pixelated structure. Some models propose that there's a kind of spacetime lattice or scaffold underneath everything. Think of it like an invisible grid of nodes and connections that forms the foundation of the universe. In this view, what we think of as empty space is actually a network, and the way these points connect and interact gives rise to the geometry of spacetime and the laws of physics as we know them. This isn't something CERN has found. It's a mathematical concept some physicists are using to try and solve the deepest puzzles out there. And one of the biggest puzzles it might help with is quantum entanglement. Entanglement is what Einstein famously called spooky action at a distance. It's when two particles become linked so their fates are intertwined, no matter how far apart you pull them. If you have two entangled electrons and measure one to have a spin up, you instantly know the other one, even if it's across the galaxy, has spin down. The information seems to travel faster than light, which should be impossible. But what if they aren't sending a signal at all? What if, on this deeper spacetime lattice, these two distant particles are actually neighbors? Their separation in our 3D space would be an illusion. The lattice could have connections, like tiny wormholes, that link distant points, creating what looks like instant communication. If that's true, entanglement is no longer spooky, it's just a natural result of the weird geography of reality's basement level. The fictional stories about a persistent anomaly in a CERN simulation tap into this exact idea. That if you could smash particles together at high enough energies, you might see a signature of this underlying grid, a kind of graininess to spacetime itself. While nobody has found this, the search is on. Experiments that detect gravitational waves and powerful telescopes are looking for tiny anomalies in the fabric of spacetime that might hint at a pixelated structure. This thinking opens the door to even bigger philosophical ideas. The physicist Vlatko Vedril argues that the most fundamental layer of reality might not be matter or energy at all, but pure information. In his view, the universe is made of quantum bits of information, and everything we see, particles, forces, even is just an emergent pattern arising from how that information is processed. Other ideas, like the holographic principle, suggest our 3D reality could be a projection of information stored on a distant 2D surface, like a hologram. These aren't proven theories. They are the speculative frontiers, where brilliant minds are trying to draw a new map of reality that finally unites the clockwork of gravity with the chaos of quantum mechanics. They're wrestling with the idea that reality isn't a thing, but a process. That what we see is just the surface of a much deeper, stranger, and more complex ocean. The grand implications, what it means for us. So, we've gone from a fictional glitch at CERN to the very real, very deep chasm in our understanding of the universe. We've seen how our solid, predictable world appears to bubble up from a ghostly, uncertain quantum realm. We've even peeked at theories suggesting spacetime itself is just an illusion. This might all sound like abstract physics, but the implications of this new view of reality are huge, and they hit right at the core of our own experience. They force us to ask the biggest questions of all. Who are we? And what are we? Take free will. We all feel like we make choices. You chose to watch this. But where does that choice come from? If our brains are just complex arrangements of particles following the laws of physics, is our feeling of freedom real? The old, deterministic clockwork universe was a nightmare for free will. If every effect is already determined by a cause, then your choices were locked in at the Big Bang. You're just a cog in a machine playing out a script that was written billions of years ago. Quantum mechanics, with its built-in randomness, seems to offer an escape. If the universe has true uncertainty at its core, if outcomes are a roll of the dice instead of a foregone conclusion, then maybe there's room for free will to act. Maybe our consciousness can somehow influence those quantum dice rolls in our brains, collapsing possibilities in a way that leads to our chosen actions. This is definitely speculative, but it shows you what's at stake. Then again, there's a more unnerving possibility. What if your choices are just the random outcomes of those quantum dice rolls, with no conscious you involved at all? In that case, you don't have free will. You just have the illusion of it, a story your brain tells itself after the fact to make sense of the quantum coin flips happening in your neurons. And what about the nature of reality itself? The idea of an underlying spacetime lattice, or a reality made of pure information, sounds a lot like another popular idea, the simulation hypothesis. If our universe is fundamentally computational, a network of information being processed, is it really a huge leap to wonder if we're living inside a giant computer? A glitch in the matrix stops being a metaphor and starts sounding like a literal bug in the code. While that's more philosophy than science right now, it shows how physics is starting to blur into questions that used to belong to philosophers and theologians. The real takeaway here is a sense of profound humility. The world is not what it seems. The comfortable reality our brains built for us is a simplified user interface. Underneath it lies a seething, complex, and probabilistic operating system that we are only just starting to figure out. The goal of physics is to peek behind that interface, to try and read the source code of the universe. And what we're finding is that reality isn't a static thing. It's an active, unfolding process. Conclusion: we started with the exciting idea of a glitch found at CERN, a crack in the wall of our reality. And while that specific story is fiction, it points to a much deeper truth. The real glitch isn't a new discovery. It's a century-old paradox at the heart of modern physics. the massive, unbridgeable gap between the solid world we see and the ghostly, probabilistic world of quantum mechanics. We've seen the impossibilities of the double-slit experiment, where one particle acts like a wave and is in two places at once. We've wrestled with the uncertainty principle, which says some things are fundamentally unknowable. We've seen how the messy process of decoherence lets our classical world emerge from that quantum chaos, like a clear picture forming out of static. And we've looked at the speculative edge, where scientists are questioning if spacetime itself is real, imagining it as a pixelated grid or a holographic projection. This story doesn't have a neat ending, because it's happening right now. It's an ongoing investigation into the biggest mystery there is. We don't have the final answers. The universe hasn't given up all its secrets. But what's clear is that our common sense view of the world is radically incomplete. The world is stranger, deeper, and more mysterious than we ever thought possible. So, I'll leave you with the same question that physicists and philosophers are asking. What do you think reality truly is at its most fundamental level? Is it a clockwork machine? A roll of the cosmic dice? A grand simulation? Or something else entirely? A layer we haven't even dreamed of yet? Drop your theory in the comments below. I would genuinely love to see what you think. And if you want to keep exploring the edges of what we know, be sure to subscribe and join us for the next one. Your brain is hiding the glitches in the universe. The smooth, continuous world we perceive is not a direct reflection of reality. It is an interpretation, a model constructed with such seamlessness that we mistake it for the thing itself. The steady flow of time, the stable presence of objects, the unbroken glide of a car down the street, all of it feels real, solid, and whole. But this feeling of smoothness is a quiet fabrication. It is similar to looking at a digital photograph. From a distance, we see a continuous image. But as we look closer, we find a grid of discrete, individual pixels. The continuity was only an appearance, an effect of distance. What if our perception of the universe operates on a similar principle? What if reality, at its most fundamental level, is not a smooth, analog film, but a collection of discrete moments and positions? This is a journey to explore that idea. We will look for the subtle discontinuities in time, in space, and in the fabric of existence itself. And we will see how the human brain works not to reveal the world in its raw, fragmented state, but to build for us a world that is coherent, stable, and predictable. Our brains did not evolve for absolute philosophical truth. They evolved for survival. A world perceived in its raw state, a storm of quantum probabilities and discrete sensory inputs, would be impossible to navigate. One could not track prey, avoid a predator, or even catch a ball if perception were a stuttering, fragmented experience. So the brain became a master editor. It takes the disjointed data from the senses and weaves it into a continuous narrative. It creates a user interface for reality that is simple, elegant, and useful. It smooths over gaps and edits out the breaks in transmission. Today, we will gently peel back the layers of that interface. Our investigation will have three parts. First, we will examine the perception of time, to see how the brain edits our internal clock. Then, we will uncover how the stable world we see is an active construction of the mind. And finally, we will turn to the source code of the universe itself, quantum mechanics, to find evidence that reality is discontinuous at its very core. The world is about to look a little different. The reconstruction of time. Let us begin with something we take for granted: the steady, forward flow of time. It feels constant, like a river moving at an even pace. But this feeling is one of the brain's most profound constructions. Our sense of a stable now is not a direct perception, but an edited reconstruction. A subtle clue to this can be found in an experience you have likely had. You glance at an analog clock, and for a brief moment, the second hand seems to freeze in place, hanging there for longer than a second before it ticks forward. This is a documented phenomenon known as chronostasis, or the stopped clock illusion. It is not time itself that is stuttering. Instead, the brain is performing a remarkable act of editing. This illusion is born from the way our eyes move. They do not sweep smoothly across a scene. Instead, they make incredibly rapid, jerky movements called saccades. During a saccade, our visual system is effectively blind. If it were not, our perception of the world would be a constant, nauseating blur. To prevent this, the brain engages in what is known as saccadic masking. It temporarily blocks visual processing during the movement. We are functionally blind for a significant portion of our waking lives, yet we never notice it. This is because the brain performs a subtle trick. When your eyes land on their new target, in this case, the clock, the brain takes that first clear image and retroactively applies it to the period you were blind. In a process known as neural backdating, it essentially determines, I was blind for the last fraction of a second, but I am looking at a clock now. Therefore, I must have been looking at this clock the whole time. The perception of that first image of the clock is stretched backward in time to fill the perceptual gap. So when you look at the clock, the image your consciousness receives is of the second hand in one position, and it holds that image for the duration of the saccade plus the present moment. This is why it appears to freeze. You're perceiving a single moment for longer than a second because your brain is using it to patch over a moment of blindness. It is a post-diction, a quiet edit of the past, performed to maintain the appearance of a continuous, uninterrupted reality. The brain's editing of time extends beyond simply patching over saccades. It also alters the nature of the present moment. Your perception of now is not an instantaneous snapshot. Instead, it is what scientists call serially dependent. The brain actively and continuously blends what you are seeing right now with what you saw a few moments ago. It is as if our perception of the present is gently pulled toward the immediate past. Studies have demonstrated this by showing subjects a series of randomly oriented patterns. Researchers found that what the subjects perceived was consistently biased towards the orientation of the pattern they had seen several seconds before. Their perception was a blend of the present and the recent past. This mechanism is what some scientists call a continuity field. It is the reason a shaky home video can appear smoother than it is, or why a brief flicker in the lights might go unnoticed. The brain is constantly averaging our perception over time to create a more stable experience. It sacrifices moment-to-moment accuracy for the sake of perceptual stability. Without this, the world might feel jittery, like a poorly streaming video. Objects might seem to flicker, and tracking anything in motion would be a disorienting task. There is a form of perceptual inertia, where the present moment carries weight from the past. This is a fundamental compromise. The brain forgoes seeing the raw, instantaneous truth of the world. In exchange, it provides a world that is stable, predictable, and smooth. It is a necessary fiction, a survival mechanism built upon a temporal adjustment. Our experience of time is not a pristine recording, it is a heavily post-processed film, edited for maximum coherence. The fabrication of visual space. If the brain's manipulation of time seems subtle, its handling of space is even more audacious. The rich, high-definition, panoramic world we believe we see is not a faithful photograph. It is a speculative reconstruction, a model built from surprisingly sparse data. Let us start with a literal hole in our vision. In the back of each eye, there is a spot where the optic nerve connects to the retina. This area has no photoreceptors. It is completely blind. This is not a tiny speck. Under the right conditions, the blind spot in each eye is large enough to make a car disappear from 100 feet away. The reason we do not perceive these two large gaps in our vision is because the brain fills them in. It is an act of pure fabrication. You can find your blind spot easily. Close your left eye and stare at a fixed point on a wall. Hold your right thumb out at arm's length to the right of that point. Now, slowly move your thumb farther to the right while keeping your eye locked on the fixed point. At a certain position, the top of your thumb will simply vanish. But you do not see a black hole. You see more wall. The brain takes the information from the surrounding area, the color, the texture, and paints it over the gap where your thumb should be. This process, called perceptual filling in, is not just about ignoring missing information. The brain is actively generating sensory data that is not there. It creates a plausible fiction based on context. It guesses what should be in the hole and puts it there, so seamlessly that we never question it. The brain does not tolerate blank spaces in its model of reality. It will invent information to ensure the world appears whole. This fabrication extends to our entire visual field. The idea that we have clear, high-resolution vision is also an illusion. In reality, only a tiny spot in the center of your vision, the fovea, can see in high detail and full color. This spot is about the size of your thumbnail held at arm's length. Everything outside of that, your peripheral vision, is incredibly low resolution and is largely devoid of color information. You can test this yourself. Pick a brightly colored object. Stare straight ahead and have a friend slowly bring the object into your peripheral vision from the side. You will notice its shape and movement long before you can correctly identify its color. You do not actually see the vivid color until it gets much closer to the center of your gaze. The world feels like it is in full color high definition all around you because the brain constructs this sensation. It takes the low-quality, blurry input from your periphery and, using memory and expectation, it creates the experience of a rich, detailed world. You assume the wallpaper pattern continues, that the grass is green. The brain does not render the details until you actually look. It runs a low-resolution simulation of the periphery and only loads the high-resolution textures when you direct your fovea to that area. Our experience of a complete, vivid visual field is a clever bit of resource management. This brings us to perhaps the most revealing aspect of our perception of space: the brain's ability to invent motion where none exists. This is not just about filling in gaps. This is about creating the dynamic experience of movement from entirely static or discrete information. A classic example is the peripheral drift illusion, seen in images like the rotating snakes. When you look at this static image, the snakes in your peripheral vision appear to be constantly rotating. But if you stare directly at any one of them, it stops. The motion only exists at the edges of your vision. The illusion arises from a complex interplay of factors: the specific, repeating pattern of luminance in the image, the tiny, involuntary movements your eyes are always making, and how different layers of neurons in your visual cortex respond. Your motion detection circuits are essentially being tricked by a carefully designed static pattern. They are firing as if they are seeing real movement, and so your brain creates the undeniable perception of rotation. An even more fundamental example is the phi phenomenon. If you flash two lights, one after the other, in close succession, you do not see two separate flashes. You perceive a single light moving from the first position to the second. Your brain invents the trajectory, the movement that connects two discrete events. These are not just curious tricks. They are profound clues. They show us that our perception of motion is not a direct registration of objects moving through space. It is a conclusion the brain reaches based on a rapid succession of discrete frames. Just like a movie creates the illusion of movement from 24 static frames per second, your brain creates the illusion of a smoothly moving world from a stream of discrete sensory inputs. The smooth, flowing reality we inhabit is a masterpiece of animation, produced in real time by the visual cortex. If this kind of calm exploration into the nature of reality helps you see the world differently, consider liking the video and subscribing to the channel. We are about to go deeper, past the constructions of the mind and down to the fundamental nature of the universe itself. This is where the world gets truly unfamiliar, and it is a place worth visiting. The discontinuous nature of reality. So far, we have focused on the ways our brains create a smooth reality. But what if the brain is doing this for a very good reason? What if it is smoothing things over because the underlying reality is not smooth at all? Let us now move from the neurology of perception to the physics of reality, from the edits in our internal software to the structure of the universe's operating system, quantum mechanics. When we speak of a glitchy universe, we are using a metaphor. The universe does not make mistakes. Rather, at its most fundamental level, it appears to be discontinuous. It is quantized. It is pixelated. And this fundamental pixelation may be the ultimate source of the discontinuities our brains work so hard to hide. In our everyday world, things seem continuous. A car can travel at 30 miles per hour, or 30.1, or 30.11. It seems to occupy any speed along a smooth spectrum. But at the quantum level, that is not how things work. Many properties, like the energy of an electron in an atom, exist only in discrete, specific packets, or quanta. An electron orbiting an atom can exist in one energy level, or a higher one, but it can never exist in between. To get from one level to the next, it must perform a quantum leap. It disappears from one energy state and reappears in another, without ever traversing the space between. It is the difference between a ramp and a staircase. On a ramp, you can stand at any height. On a staircase, you can be on step 1, or step 2, but never on step 1.5. The universe, at its smallest scale, is a staircase. This leads us to the most famous experiment in all of physics, the double-slit experiment. It reveals a property of reality so profound that it forces us to question the nature of existence itself. You fire particles, like electrons, one at a time, toward a barrier with two slits. Behind the barrier is a screen that records where each electron lands. If electrons were like tiny, solid objects, you would expect two bands on the screen, corresponding to the slits. But that is not what happens. The electrons land on the screen in an interference pattern of many bands. This is the pattern waves make. It is as if each single electron, traveling alone, somehow passes through both slits at once, interfering with itself like a ripple in a pond. The particle behaves like a wave of pure potential. Now for the truly strange part. If you place a detector at the slits to see which one the electron goes through, the game changes. The moment you observe its path, the interference pattern vanishes. The electrons start behaving like solid objects again, and you get just two bands on the screen. The very act of measuring the particle's path forces it to assume a single, definite state. When it is not being looked at, it is a wave of possibilities. When it is a single, discrete particle. This is wave-particle duality. The fundamental nature of a particle, whether it is a diffuse wave or a concrete object, depends on whether it is being measured. An even more radical version of this is the delayed choice experiment. The setup is similar, but with a twist. We let a particle pass through the slits while we are not watching. At this point, it should be behaving like a wave. But after it has already passed the slits, we make a last-second decision. We can either do nothing, in which case we see a wave pattern. Or, at the very last moment, we can insert special lenses that allow us to figure out which path the particle took. The unbelievable result is this. The choice you make in the present determines what the particle appears to have done in the past. If you choose to measure the path, the particle behaves as if it had gone through only one slit all along. If you choose not to, it behaves as if it had gone through both. This experiment does not prove that we are sending information back in time. The standard interpretation is even stranger. It suggests that a property like the path the particle took has no real meaning or existence until it is measured. The universe does not pre-record a history. The past of a particle is just as undefined as its future. Reality remains an open-ended superposition of possibilities until an interaction forces a particular history to become real. The discontinuity here is the very concept of a single, objective past. Just as the brain retroactively fills in a perceptual gap, the universe seems to only render a definite history when an observation demands it. A synthesis of perception and physics. We have seen two parallel stories. In one, the brain is a reality-generating machine, taking discrete sensory data and smoothing it into a continuous experience. In the other, the universe, at its core, is a discontinuous, probabilistic system that only snaps into a discrete state upon interaction. Let us now ask the ultimate question. Are these two stories connected? Could the brain's smoothing function be an evolutionary response to the discontinuous nature of reality? Here, we step onto the frontier of science and philosophy. It is important to be clear. There is currently no direct, testable scientific evidence linking the mathematics of quantum mechanics to the specific neural processes of perception. This is a speculative leap, a metaphorical bridge we are building to see reality from a new perspective. With that crucial caveat in mind, consider this framework. The universe, at its most fundamental level, presents a constant stream of quantum events, a superposition of possibilities. Through a process called decoherence, the interaction of a quantum system with its environment, this wave of possibilities collapses into a single, definite, discrete outcome. This is the moment a wave becomes a particle, a probability becomes a fact. This is the universe rendering one frame of its slideshow. Now, what does the brain do? It is bombarded with the results of these countless collapses, a torrent of discrete data points from our senses. It receives a frame-by-frame account of reality. Through processes like chronostasis, it papers over the temporal gaps. Through serial dependence, it blurs frames together, creating the illusion of smooth motion. Through perceptual filling in, it patches the spatial holes in the data. In this view, the brain's job could be seen as that of a quantum to classical converter. It is a biological machine designed to take the discontinuous output of the universe and format it into a continuous, stable reality that a large organism can navigate. It is a continuity-generating engine living in a frame-by-frame universe. The perception of a smooth, gliding car is not a lie because the car is actually stuttering. It is an interpretation because the very concepts of smoothness and gliding are high-level constructs the brain creates. At the fundamental level, there is just a sequence of discrete states that our brain has skillfully animated into the experience of motion. Living in the interpretation. Today, we have journeyed from the quiet workings of our own minds to the deepest laws of the cosmos, and we have found a similar pattern at every level. The smooth, stable world of our experience is a carefully crafted interpretation. We learned that our brain edits our perception of time, using the stopped clock illusion to fill in gaps and serial dependence to average the past with the present, creating a stable but less than literal flow of time. We discovered that our perception of space is a fabrication. Our brain conceals a blind spot by painting over it with information from the surrounding area and creates the feeling of a rich periphery from blurry, colorless data. Most profoundly, it invents the very sensation of motion from discrete images. And finally, we explored the quantum realm, where we found the source of this discontinuous reality. We saw that the universe is fundamentally quantized, and that reality itself seems to wait for observation before collapsing from a wave of potential into a definite particle. The grand takeaway is this: your brain is not a passive receiver of information. It is an active interpreter. It evolved not to show you the truth in all its raw, discontinuous glory, but to create a simplified, useful, and continuous user interface. The world does not look like a choppy slideshow precisely because of the brain's hidden power to edit out the cuts and present us with a beautiful, coherent film. The illusion of continuity is not a flaw in our perception. It is perhaps its greatest achievement. It is the feature that allows a mind, born from quantum uncertainty, to make sense of the world. So, the next time you watch a sunset seemingly flow across the sky, or see a bird glide effortlessly through the air, it is worth asking, am I seeing reality as it is? Or am I watching the elegant interpretation my mind has produced for me? What other quiet truths might be hidden within our own perception? If this exploration has changed the way you see the world, even a little, consider subscribing. We explore the boundaries of reality and the human mind, and there is always more to understand. Why nothing in the universe is truly random. You've probably heard that the universe is a cosmic casino, governed by the roll of the dice. That from the smallest particle to the grandest galaxy, it's all just random. But what if that's the biggest illusion we've ever bought into? What if I told you that every single event, from an apple falling to the thoughts in your head, was locked into place from the beginning of time? In this video, we're going to tear down the idea of chance and ask a pretty terrifying question. Is anything in the universe truly random? Look around. The world feels like a beautiful mess, doesn't it? The way milk blooms in your coffee, the specific path a leaf takes as it flutters down from a tree, the chaotic buzz of a city street. All these things feel unique, unpredictable, random. We talk about chance encounters and lucky breaks like they're real forces shaping our lives. Even our own minds feel like masters of spontaneity. Quick, think of a random string of numbers. Got it? Well, chances are, the sequence you just came up with wasn't random at all. Our brains are pattern-seeking machines. Even when we try to be unpredictable, we fall back on familiar habits. We avoid repeating numbers, we try to spread them out, creating something that looks random to us, but is really the output of a predictable mental process. This is the illusion of randomness. We're so caught up in what we see as chance, we barely stop to ask if it's even real. We see faces in the clouds and patterns in stock market noise because our brains are desperate to find meaning. But what if the noise is just a signal we haven't figured out how to read yet? What if the whole universe isn't a game of chance, but a machine of unimaginable complexity, where every single action is the direct, unavoidable result of the one that came before it? This idea isn't new. It's a concept called determinism, and it's been haunting scientists and philosophers for centuries. The foundation of order. To get our heads around this clockwork universe, we need to travel back to the 17th century, to the father of classical mechanics, Sir Isaac Newton. Newton's laws of motion were a complete game-changer. They painted a picture of the universe as a grand, predictable machine. For the first time, we had a mathematical toolkit that could actually predict the future. With just a few equations, we could map the arc of a cannonball, the orbit of the moon, and the return of a comet. The universe, it seemed, was governed by fixed, unbreakable laws. If you know the starting position, speed, and all the forces acting on an object, you can, in theory, know its entire future. This is the heart of classical determinism. The idea that the future is just a calculable consequence of the past. This powerful idea was pushed to its absolute limit in the early 19th century by the French scholar Pierre-Simon Laplace. He imagined a vast intelligence, an entity that could know the exact location and momentum of every particle in the universe at one single moment. This being, later nicknamed Laplace's demon, would be a cosmic supercomputer. Armed with this perfect snapshot of the present and Newton's laws, the demon could calculate the entire future of the universe with total certainty. For this intelligence, nothing would be uncertain. The past and future would be laid out like an open book. From a butterfly's wingbeat to the birth and death of stars, every event would just be a matter of calculation. In this vision, the universe is like a cosmic game of pool. Once the cue ball strikes, the path of every other ball is set. No chance, no luck, just a cascade of cause and effect. For Laplace and many thinkers of his time, this wasn't just some philosophical thought experiment. It was the direct conclusion from the science of the day. They believed that words like chance or randomness were just labels we put on our own ignorance. A coin flip only seems random because we can't possibly know the precise force of the flick, the exact spin rate, the tiny currents of air, and the angle of impact. If we could measure all those variables, the outcome, heads or tails, would be perfectly predictable. In the classical view, randomness isn't a real feature of the universe. It's just a reflection of our own limited minds. It's an incredibly powerful worldview. It describes a universe that's rational, ordered, and, ultimately, something we can understand. It suggests that everything happens for a reason, not in some mystical way, but in a purely mechanical one. Every effect has a cause, stretching back in an unbroken chain to the Big Bang itself. And if you follow that chain forward, it dictates everything that will ever happen. In this clockwork reality, there are no surprises. No miracles. Just the relentless, predictable ticking of physical law. But this neat and tidy vision, which dominated science for over 200 years, was about to meet its match. Even before the main event, cracks were showing. Scientists stumbled upon something called chaos theory, which revealed that even in simple, deterministic systems, a tiny, immeasurable difference in the starting conditions could lead to wildly different results down the line. This is the famous butterfly effect. It meant that long-term prediction was practically impossible, even if the underlying laws were deterministic. It got so serious that in 1986, the eminent mathematician Sir James Lighthill issued a public apology on behalf of his field. He stated that physicists had misled the general educated public by spreading ideas about the determinism of systems satisfying Newton's laws of motion that were to be proved incorrect. But this was just a tremor. The real earthquake was about to come from the strange and fuzzy world of the very, very small. The Great Objection. In the early 20th century, physics got weird. A new theory, quantum mechanics, popped up to explain how things work at the atomic and subatomic level, and its discoveries were mind-bending. Down at this tiny scale, Newton's clean, predictable rules just fall apart. Particles like electrons don't have one definite position or one definite momentum. Instead, they exist in a fuzzy cloud of possibilities called a superposition, a blend of all possible states at once. Think of it like a spinning coin. While it's in the air, it's not heads or tails, it's a blur of both. Only when it lands, when we measure it, does it pick one. This is called the collapse of the wave function. And here's the kicker. According to quantum mechanics, you can't predict the outcome of any single quantum event with certainty. You can only calculate the odds. Take a radioactive atom. We can calculate its half-life with stunning precision, so we know exactly how long it'll take for half of a big pile of these atoms to decay. But for any one atom, it is fundamentally impossible to predict when it will decay. It could be in the next second or in a billion years. The process appears to be genuinely, fundamentally random. This isn't like the coin flip, where we're just ignorant of the details. Quantum randomness seems to be baked into the fabric of reality itself. This is all wrapped up in Werner Heisenberg's famous uncertainty principle. It states there's a hard limit to how precisely we can know certain pairs of a particle's properties at the same time, like its position and its momentum. The more you know about one, the less you know about the other. Imagine trying to see an electron with a super-powered microscope. To see it, you have to bounce a particle of light, a photon, off it. But the electron is so tiny that the very act of hitting it with a photon knocks it way off course, changing its momentum in an unpredictable way. It's not a problem with our tools, it's a law of nature. You can know where a particle is, or you can know where it's going, but you can never, ever know both perfectly. This throws a giant wrench in the gears of Laplace's clockwork universe. If you can't know the precise position and momentum of every particle, you can never predict the future. The demon is defeated, not by a lack of computing power, but by a fundamental law of physics. It looked like determinism was dead. This was so bizarre that it led to one of the most famous quotes in the history of science. Albert Einstein, who ironically helped start the quantum revolution, could never accept its probabilistic nature. He famously declared, "God does not play dice with the universe." He was convinced that the apparent randomness was just a sign that our theory was incomplete. There must be, he argued, hidden variables, deeper, undiscovered properties that, if we knew them, would make everything predictable again. The mainstream view, the Copenhagen interpretation, pushed back, arguing that a particle's properties literally don't exist until we measure them. The randomness is real. For decades, this was mostly a philosophical debate. But then a physicist named John Bell devised a mathematical test, which was later performed in labs, that could actually distinguish between the two ideas. The results have been clear and repeated. Einstein's idea of local hidden variables was wrong. The universe, at its most fundamental level, really does seem to play dice. But the story might not be over. Some recent 2026 findings are starting to probe the edges of this concept, with MIT experiments demonstrating a way to bias and control quantum randomness using vacuum fluctuations, suggesting it's not an untouchable force. Other speculative ideas, like the resonant universe framework, propose that what seems random to us might be modulated by cosmic scale influences. Other interpretations try to sidestep the randomness. The many worlds interpretation suggests the universe splits every time a quantum measurement is made. In one universe, the coin lands heads, in another, it's tails. You split too, with one version of you seeing each outcome. This saves determinism for the multiverse as a whole, but for any one of us in a single branch, things still look random. So, we're left at a crossroads. Classical physics gives us a predictable machine. Quantum physics gives us a world built on irreducible chance. How can both be true? The revelation. The answer to this paradox is a concept as beautiful as it is powerful: emergence. Emergence is the idea that complex systems can develop new properties and obey new laws that aren't present in their individual parts. A single molecule of H2O isn't wet. A single neuron isn't conscious. A single bird doesn't flock. Wetness, consciousness, and flocking are emergent properties. They arise from the complex interactions of many simple components. The whole becomes greater than the sum of its parts. This is the bridge between the random quantum world and our predictable classical world. The random, unpredictable jiggling of countless individual particles, when you zoom out, averages out to create the smooth, predictable laws we see every day. A core idea in statistics, the law of large numbers, explains this. A large number of random events will produce a highly predictable average. Think about the sound of rain on a roof. Each individual raindrop hits a random spot at a random time, an unpredictable plink. But the combined sound of a downpour is a steady, predictable roar. The randomness cancels out, and a stable pattern emerges. This isn't just a nice metaphor, it's a core principle of physics. The field of statistical mechanics explains how properties like the pressure and temperature of a gas emerge from the chaotic motion of billions of individual molecules. No single atom has a temperature. Temperature is an emergent property. It's the average kinetic energy of all those particles. You can't predict the path of one gas molecule, but you can predict the pressure of the whole gas with near-perfect certainty. Microscopic randomness gives rise to macroscopic predictability. We see this everywhere. When water freezes into ice, the individual molecules are all jiggling randomly. But as the temperature drops, a new, collective order suddenly emerges, and they lock into a crystal lattice. Out of the chaos of trillions upon trillions of interacting electrons inside a crystal, a miraculous thing can emerge: a quasi-particle. This is a collective excitation, a ripple in the sea of electrons, that behaves just like a single, simple, well-behaved particle. It moves in a straight line with a constant speed as if it were all alone in empty space. It's a phantom, but it follows simple, predictable rules. The messy, random quantum world gives rise to an effective, macroscopic world governed by what we can call adequate determinism. Some theories, like emergence theory, take this even further, proposing that everything we experience, space, time, particles, all of it, emerges from a more fundamental reality. One speculative idea pictures the universe at the tiniest possible level, the Planck scale, as a kind of pixelated information network, maybe a geometric crystal built of tiny tetrahedra. From the simple rules governing these pixels, the laws of physics as we know them might emerge, like an operating system booting up from binary code. So, is the universe random? It seems the answer is, it depends on your zoom level. At the fundamental quantum level, events seem irreducibly probabilistic. But this is a structured, mathematical randomness. And it's this very randomness that, when taken all together, allows for the stable, ordered, and predictable world we live in to emerge. The chaos at the bottom doesn't break the order, it creates it. The randomness isn't a bug, it's a feature. It's the raw material from which the illusion of certainty is built. The grand implications. If our orderly world is just an emergent property of randomness, what does that mean for us? For our lives, our choices, our sense of self? This is where physics smashes into philosophy. Let's start with luck. That chance encounter that led to a lifelong friendship? From the perspective of an emergent, deterministic world, it was the inevitable result of two complex life paths. Every decision made, every influence felt, converging at a precise point in space-time. It wasn't luck, it was the result of an equation too complex for us to solve. Success, then, might not be about catching lucky breaks. It's about positioning yourself so the deterministic unfolding of events is more likely to intersect with your goals. As the old saying goes, the harder I work, the luckier I get. You're aligning your own deterministic path with the paths of the opportunities you want. This leads us to the big one, free will. Is it real? The feeling that we are the authors of our own actions is core to being human. But is it just another illusion? Neuroscientific experiments, like those pioneered by Benjamin Libet, famously showed that brain activity linked to a decision can be spotted seconds before the person is consciously aware of making the choice. This suggests what we experience as a conscious decision might just be the tail end of unconscious neural processes. But it's not an open and shut case. The exact implications of these findings are still hotly debated among neuroscientists and philosophers today. This aligns with the idea of your brain as a fantastically complex physical system. It's made of 86 billion neurons, all firing according to the emergent laws of chemistry and electricity. Your thoughts and decisions are emergent properties of this network. They aren't a ghost in the machine, they are the machine running. And if the machine runs on deterministic laws, then its outputs, your choices, are also determined. So are we just puppets dancing on the strings of cause and effect? Not necessarily. Perhaps free will itself is an emergent property. Just as wetness emerges from water molecules, maybe the ability to make meaningful choices emerges from the staggering complexity of the brain. This view, called compatibilism, says free will and determinism can coexist. A free choice isn't an uncaused one. It's one that's caused by your internal beliefs and desires, without outside coercion. You're acting on your will, even if that will is itself the product of a long chain of causes. This perspective doesn't have to be disempowering. It offers a sense of profound connection. It dissolves the barrier between me and the universe. Your thoughts aren't random sparks. They are the product of everything that has ever happened, a continuation of the unbroken causal chain from the Big Bang. Every choice you make ripples forward, becoming part of the fabric that will shape the future of the cosmos. We started by asking if anything is truly random. We went from Newton's clockwork world to the quantum casino, and landed at the grand synthesis of emergence, where order is born from chaos. We've seen that the randomness of our daily lives is mostly an illusion born of complexity, while the true randomness at the heart of reality is the very engine that builds our stable, predictable world. The deterministic nature of this reality doesn't rob life of meaning. It does the opposite. It places you firmly inside the grand, unfolding story of the cosmos. Your actions aren't meaningless accidents. They are the necessary consequences of the universe's entire history, and they are the necessary causes of its entire future. You aren't a ghost in the machine. You're the machine, experiencing itself. The illusion isn't that the universe is ordered. The illusion is that we are somehow separate from that order. So the next time you watch milk swirl into your coffee, remember the deep truth hidden beneath the apparent chaos. There is a profound, underlying order to everything, an unbroken chain of cause and effect stretching from the beginning of time to its end. And you are a vital, inseparable, and determined part of it. What you choose to do next was always going to happen, and it will change everything. If this journey through reality sparked something in you, consider subscribing for more deep dives into the biggest questions out there. And let me know in the comments, does thinking about an emergent, deterministic universe change how you see your own life? I'd love to read your thoughts. Your eyes literally create the world around you. There is a world you are sitting in right now. You can see the walls, the furniture, the light from the screen. It all feels solid, real, and perhaps most importantly, separate from you. There is a deep, quiet assumption that it was all here long before you looked, and it will remain long after you look away. In this view, our eyes are passive windows, simply recording a reality that is already finished, a world we are only visiting. But what if that feeling, that intuitive sense of a solid and separate world, is not the full story? What if the foundation of reality is far stranger, and far more connected to us, than we have ever imagined? This is not a question of philosophy, but of physics. It is a story that begins when science peered deeper than ever before into the architecture of matter, and found that the world we see is not something we merely find, but something we participate in. The simple act of looking is not just seeing, it is an interaction that helps shape what becomes real. By the end of this journey, we will see that we are not just observers of the universe. We are the means by which the universe, in a way, observes itself. The foundational crack. Let's begin with the world we trust, the classical world. It is a place of certainty, where cause and effect move in a predictable line. A book, when pushed, will fall. A ball follows a reliable arc. In this world, described by the physics of Isaac Newton, everything has a definite place. Objects are solid things. A chair exists as a chair, whether we are in the room or not. Its existence is not a matter for debate. This is the assumption that allows us to navigate our lives. We are spectators, watching events unfold according to understandable laws. For centuries, this was the unshakable foundation of science. We could measure the universe, learn its rules, and predict its behavior, all without truly disturbing it. The scientist was a detached chronicler, an invisible witness. The universe, it seemed, did not care if it was being watched. But at the turn of the 20th century, as our tools grew powerful enough to look into the hidden structure of things, into the realm of the atom and what lies within, we found a crack in that foundation. Scientists expected to find a miniature version of our own world, tiny planets orbiting a tiny sun. Instead, they found something that looked more like a ghost. They found a world of pure, shimmering potential. A world that refused to be pinned down. A world that seemed to change when it was observed. The journey into this place begins with a simple experiment. A setup so basic you could almost build it at home. And yet, its results are so unfamiliar, so contrary to our everyday logic, that the physicist Richard Feynman once said it holds the central mystery of quantum mechanics. It is called the double-slit experiment, and it is the first quiet step toward understanding how our world is summoned into being. The mystery of the two doors. Imagine a blank wall. In front of it, we place a barrier with two thin, vertical slits. And in front of that, a device that can fire tiny objects, one by one. First, let's use something familiar, like marbles. If we fire marbles at the barrier, some will bounce off, but others will pass through one slit or the other. The pattern they make on the back wall is simple. Two bands of hits, one behind each slit. This is a pattern of particles, of solid things following definite paths. There are no surprises here. Now, let's change the experiment and use waves in a tank of water. As the waves spread out, they pass through both slits at the same time. These two new waves then ripple into each other. Where two crests meet, they create a bigger wave. Where a crest meets a trough, they cancel out. The pattern this creates on the back wall is not two bands, but many. It is a distinctive interference pattern with alternating stripes of high and low intensity. This pattern is the unmistakable signature of a wave. It can only be made if something passes through both slits at once and interferes with itself. So, we have two clear results. Particles make a two-band pattern. Waves make a multi-band interference pattern. Now, for the moment that changed our understanding of reality. We return to our device, but this time, it will fire electrons, the tiny particles that form atoms. We will fire them one at a time. An electron is a particle, a small speck of matter. So we expect it to act like a marble. Each one should go through either the left slit or the right, and over time, build up two bands on the wall. The experiment begins. We fire one electron. It makes a single dot on the screen. A second electron makes another dot. Then a third, and a fourth. At first, the pattern looks random. But as thousands, then millions of these individual impacts build up, something quietly impossible begins to emerge. It is not the two-band pattern of particles. It is the multi-band interference pattern, the signature of a wave. Let this sink in. We are firing single electrons. There is nothing for them to interfere with. And yet, they are forming a pattern that could only be made if each electron passed through both slits at the same time and interfered with itself. It's as if you walked toward two doors, passed through both at once, and your two selves bumped into each other on the other side. It does not make sense in our world. The physicists who first saw this were deeply confused. They decided they had to look. They placed a detector at the slits to see which path each electron actually takes. A simple act of observation. Which door is it going through? They turn on the detector and run the experiment again. The detector works. The first electron goes through the right slit. The second, through the left. The third, left again. Now they know the path of every single electron. They are behaving like well-behaved particles, each choosing one definite path. They let the experiment run, collecting millions of these observed electrons. But when they looked at the final pattern, the interference pattern was gone. Completely. In its place were two simple bands. The pattern of particles. The very act of watching, of measuring which slit the electron went through, forced it to behave like a particle. It was as if the electron knew it was being observed. When no one was looking, it existed in a ghostly state of potential, a wave of probability that could go through both slits at once. But the moment you asked the question, which way did you go? Reality seemed to choose. The wave of possibilities collapsed, and the electron became a definite thing at a definite place. This is the observer effect. The discovery that, at the quantum level, the universe does not seem to possess definite properties until we measure them. Before the measurement, the electron is not a tiny ball. It is a superposition, a fuzzy cloud of all its possibilities at once. But the act of observation is not passive. It is an interaction. It forces that cloud of potential to resolve. It turns the maybe into an is. The revelation. What does it mean to look? The implications of this are quiet but staggering. They lead to a more fundamental question. What counts as an observation? Does it require a conscious human being? For decades, this was a point of deep debate. But as our understanding grew, the answer turned out to be both simpler and more profound. An observation is any interaction that extracts information. It doesn't need a mind or consciousness. The detector at the slit was just a machine. Bumping into an air molecule, being struck by a photon of light, any physical entanglement that reveals a particle's path is enough to force a choice. You cannot touch a quantum system without fundamentally changing it. Imagine trying to measure the temperature of a single drop of water with a hot thermometer. The thermometer itself alters the temperature you are trying to measure. At the quantum scale, this effect is not a matter of clumsy equipment, it is an unbreakable law of nature. There is no such thing as a truly passive observer. The universe, at its most basic level, is a participatory system. To look is to touch. To measure is to interact. This principle leads to one of the most fascinating phenomena in all of physics, the quantum Zeno effect. It's named after an ancient Greek paradox about an arrow in flight. At any single instant, the arrow is not moving, it is just at one spot. So if time is made of these instants, how does the arrow ever move? In our world, this is a philosophical game. But in the quantum world, it is literally true. Imagine an unstable atom that will eventually decay. This is a quantum process. But what happens if you watch it? What if you measure it over and over again, very rapidly, constantly asking the question, have you decayed yet? Each time you measure it and find it has not decayed, you're forcing its wave function to collapse back into the undecayed state. You reset the clock on its decay. If you make these observations frequently enough, you can essentially hold the atom in place. You can prevent it from evolving. You can, in a literal sense, make a watched pot never boil. This isn't a theory. It has been confirmed in laboratories. Physicists have used frequent measurements to freeze quantum systems, preventing atoms from changing. In experiments at Cornell University, for instance, scientists cooled a gas of atoms to near absolute zero, where they began to behave quantum mechanically. When the scientists shone a laser on the atoms to watch them, their quantum movement stopped. The constant observation pinned them down. Think about what this means. Observation doesn't just reveal what is there, it holds it in place. The unobserved world is a flowing river of possibilities. The act of looking, of interacting, forces that river into a fixed channel. It turns the dynamic flux of potential into the stable world of our experience. But if our world is made of these quantum building blocks, why don't we see this strangeness in our everyday lives? Why does a coffee mug stay a coffee mug? The bridge between the ghostly quantum realm and our solid reality is the final and most crucial piece of the puzzle. From quantum dust to solid ground. The reason you don't see a chair in a superposition of states is because it's impossible for it to remain in one. A quantum system can only maintain its strangeness if it is perfectly isolated from the rest of the universe. The moment it interacts with anything, the game is up. And an object like a chair, or even a speck of dust, is never, ever isolated. It is being constantly bombarded by trillions of air molecules every nanosecond. Photons from the lights in the room are bouncing off it. Each of these interactions is a tiny measurement. Each collision asks the chair, "Where are you?" And each collision forces an answer. This process is called decoherence. It is a great leak of quantum information into the environment. A single, isolated electron can be a fuzzy wave of potential. But the moment it bumps into an air molecule, information about its position is imprinted on that molecule. That molecule then bumps into another, and the information spreads like a rumor, exponentially fast. Within a fraction of a second, any quantum superposition the chair might have had is destroyed. The information about its definite position, here, and not there, has leaked out and become entangled with the entire room, and then the entire planet. The quantum weirdness is diluted into a vast ocean of environmental interactions, leaving behind only one stable, classical reality. This leads to a quiet and powerful idea known as quantum Darwinism. It suggests that reality emerges through a process of cosmic natural selection. The environment isn't just a disruptive force, it's a selective amplifier. Of all the possible states a system could be in, only certain pointer states are stable enough to survive the constant questioning of the environment. They are the fittest states. They are robust, and they are able to imprint many copies of themselves onto their surroundings without being destroyed. The environment acts like a massive cosmic broadcast. It monitors every object and preferentially selects these stable, classical states, copying their information and sending it everywhere. The reason we all agree an apple is red is because red is a stable pointer state. Its molecular structure interacts with light in a way that redundantly imprints that information onto trillions of photons. These photons travel to your eyes and to mine. We are all receiving a copy of the same, stable, redundantly broadcast information. Reality appears objective because we are all tapping into the same broadcast, the consensus reality forged by decoherence. So, in a very real sense, the universe is constantly observing itself. The endless dance of particles and energy is a web of interactions that resolves quantum strangeness at the large scale and gives birth to the solid, predictable world we know. No conscious observer is required. But this does not remove us from the story. It places us at the very pinnacle of this process. For while any interaction is a measurement, the act of a conscious mind observing the world is the most sophisticated form of measurement we know. The new reality, the participant. We have traveled from the solid world of our assumptions, down into the ghostly realm of quantum potential, and back up again, to see how the classical world emerges. We have learned that reality is not a static object but an active process. The universe, through decoherence, creates a stable, objective reality. But we are not separate from that universe. Our bodies are collections of atoms participating in this cosmic dance. Our brains are webs of electrochemical interactions, machines of unimaginable sensitivity. When you look at the world, you are not just a passive receiver of the information the universe broadcasts. You are a final link in the chain. The physicist John Archibald Wheeler called this the participatory universe. He argued that we live in a universe that is brought into being, in some sense, by the participation of those who observe it. He summarized this with the phrase, it from bit, the idea that every physical thing, every it, derives its ultimate existence from the information captured by acts of observation. This reframes our place in the cosmos. We are not simply passive witnesses to a finished world. We are participants. Your life is not a film you watch, but a reality you are actively engaged with through every glance, every thought, every choice. The universe is not a noun, it is a verb. It is a process of becoming, and we are at the cutting edge of that process. We began with a simple idea that the world is out there, and we are in here. We end with a truth that is far quieter and more humbling. The universe beneath our feet is a shimmering, uncertain sea of potential. The solid world we touch and see is not a given. It is a construction, built from an endless chain of interactions that begins with the jiggling of atoms and ends with us. Our eyes are not just cameras. They are participants. They are part of the process that turns waves of pure potential into the definite, experienced reality of the world around us. The world we experience is a collaboration between the vast potential of the cosmos and the focusing lens of awareness. We are not just a piece of the universe. We are the part of the universe that has woken up and is looking back at itself. And in that look, it is bringing itself into being. So, the next time you open your eyes, you might remember what is truly happening. You are not just seeing the world. You are meeting it. If this quiet exploration into the nature of reality has offered you a new perspective, consider subscribing for more journeys to the edge of what we know. The universe is far stranger, and we are far more connected to it than we have ever been told. The universe doesn't believe in your choices. You wake up. Perhaps you choose to stay in bed for a few more minutes. Later, you choose one shirt over another. Each of these moments feels like a quiet decision, a point in time where your own awareness seems to guide the course of your day. It feels as though each choice, no matter how small, carves a path into the future that would not have existed otherwise. This unfolding of cause and effect is not just a feeling. It is the texture of our reality. It's how we understand our lives. You are the author of your actions, and your actions seem to shape what comes next. But this story, as clear as it feels, begins to change when we look closer. What if this deeply familiar sense of cause and effect is an emergent feature of the world, not its fundamental rule? What if, as we zoom down to the level where the universe is written, the very idea of a cause, leading to an effect, quietly dissolves? The idea feels unfamiliar. It seems to go against our direct experience. And yet, it's a possibility that has been gently explored by physicists and philosophers for over a century. The quiet suggestion is that causality, the rule that a cause must come before its effect, is not a basic law of the universe. It is a pattern that appears only at our scale, the large, complex, macroscopic world we inhabit. This isn't just an abstract thought. It touches on our sense of self. If the universe, at its core, doesn't distinguish between a cause and an effect, if it doesn't hold the same arrow of time that we feel so clearly, then what does that mean for our choices? For our feeling of agency? Today, we're going on a journey to the foundations of our world. We will look past the surface of our comfortable, cause and effect reality and into the quiet strangeness of fundamental physics, where time can seem to flow in both directions and the future might be reflected in the past. We'll explore how something as solid as causality can arise from a world that does not seem to contain it. And in the end, we may find that our place in the cosmos is far quieter and far more strange than we ever imagined. An unfolding event. Let's begin with a simple observation. A coffee cup slips from a hand and breaks on the floor. It seems to be a clear case of cause and effect. The cause: the cup was let go. The effect: it fell and shattered. The sequence is direct, clear, and moves in only one direction. We never see the opposite. We do not witness scattered pieces of ceramic on the floor gather themselves together, leap up into a hand, and fill with warm coffee. That would feel like a violation of natural law. Or would it? This is where our intuition begins to separate from the physics that describes our universe. If we were to film the cup breaking, anyone watching would know instantly if the film was playing forward or backward. The forward version shows an ordered object becoming disordered. The backward version shows disorder spontaneously creating order. One is reality, the other seems impossible. This direction, this one-way path from past to future, is what we call the arrow of time. We feel, intuitively, that causality is what gives this arrow its direction. A cause happens, which forces an effect to happen, and this pushes time forward. But here is the first quiet puzzle. The most fundamental laws of physics we know, the equations describing motion, gravity, electromagnetism, and even quantum mechanics, are almost all time symmetric. They work just as well played forwards in time as they do backwards. What this means is that if you were to watch a recording of planets orbiting a star, or two billiard balls colliding, you could not be certain if the recording was playing forward or backward. The reversed version of events is just as possible, just as consistent with the fundamental laws as the original. According to these laws, there is no built-in before or after. There are just different states of a system at different times, and the laws describe the relationship between them. The equations themselves do not care which way you travel along the timeline. The philosopher Bertrand Russell noted this more than a century ago, pointing out that the idea of cause, so important to us, seems to be absent from the basic rules of physics. Physics describes patterns and relationships, how a system evolves from one state to another. From this perspective, saying, the cue ball striking the 8 ball caused it to move, is no more fundamental than saying, the 8 ball moving in reverse caused the cue ball to recoil. Both are valid ways of describing the same event according to time-symmetric laws. This creates a deep question. Our lived experience is overwhelmingly directional. Cups break but do not unbreak. We remember the past, but we do not remember the future. If the underlying laws are symmetric, where does our one-way world come from? The answer seems to be found not in a strict law, but in a statistical tendency. It is called the second law of thermodynamics. This law observes that in a closed system, entropy, a measure of disorder or randomness, tends to increase over time. An intact coffee cup is a state of low entropy. It is ordered. Its molecules are arranged in a very specific, structured way. The shattered cup on the floor is a state of high entropy. It is disordered. Its molecules are scattered. There are vastly more ways for a cup to be in a disordered, broken state than in a single, ordered one. So when the cup falls, it is not being forced forward by a law of causality. It is simply moving from a statistically improbable ordered state to an overwhelmingly probable disordered one. The universe is not pushing it, it is just settling into a more likely arrangement. The arrow of time, it seems, is not the arrow of causality. It is the arrow of entropy. It is the universe's slow, steady movement from order toward disorder. This is a profound realization. It suggests our sense of forward-moving time, and our idea of cause and effect, is not a feature of the universe's basic mechanics. It is a feature of the universe's state. Specifically, it stems from the fact that the universe began in a very, very low entropy state, a highly ordered arrangement at the Big Bang. We are living in the expanding, cooling, and disordering aftermath. The reason we see cups shatter but not reassemble is the same reason we see the universe expand but not contract. We are on the slope of a great statistical hill, and for us, time flows downhill, from order to disorder. This gently decouples causality from the most basic laws of physics. It reframes it as a macroscopic, statistical pattern. Our sense of A causing B is a result of living in a world where things, overall, are becoming less orderly. But this is only the first part of the story. When we travel from this large-scale world into the realm of the very small, the question of causality becomes stranger still. If the classical world makes causality look like a statistical pattern, the quantum world seems to remove it altogether. The quantum fading. If the time-symmetric laws of classical physics felt unfamiliar, the quantum realm is a place where our everyday ideas of reality are quietly set aside. Here, at the scale of atoms and particles, the predictable world of definite objects gives way to a world of probability and deep strangeness. And the idea of a clear chain of cause and effect does not just become blurry, it seems to fade into a fog of potential. In our world, things are definite. A cup is either on the table or on the floor. It has a specific location. If we know its position and momentum, we can use the laws of physics to predict its path. This was the dream of classical physics. The state of the world at one moment determines its state at all other moments. Quantum mechanics dissolves this dream. It suggests that a particle, like an electron, does not have a definite position until it is measured. Instead, it exists in a superposition of all its possible states at once. It is a wave of probability. The math of quantum mechanics does not tell you where the particle is. It tells you the probability of finding it in a particular place if you look. Think about that for a moment. The past state of a particle does not determine a single future outcome. It determines a range of possibilities. When a measurement is made, this wave of possibilities collapses into one definite reality. But which one? The theory only gives the odds. It is as if the universe holds its breath at every quantum interaction before settling on what happens next. This is a fundamental challenge to the classical idea of cause. If the same initial state can lead to different effects with only statistical predictability, The necessary link between a cause and its effect is broken. Deterministic causality does not seem to hold at this most fundamental level. But the quiet strangeness continues. Let's consider something Albert Einstein once called spooky action at a distance, quantum entanglement. Imagine you create a pair of particles whose properties are linked. For instance, their spins must be opposite. If one is found to be spin up, the other must be spin down. Now, you send these two particles in opposite directions, across a room or across a galaxy. According to quantum mechanics, neither has a definite spin until it is measured. Both exist in a superposition of possibilities. The moment you measure the first particle and find it is spin up, you instantly know that the second particle, no matter how far away, is now spin down. The wave of possibilities for both particles collapses at the same time. Information seems to be shared between them faster than the speed of light, which is something Einstein's theory of relativity says should not happen. This apparent violation of local causality, the idea that an effect cannot happen faster than a cause can travel to it, is one of the deepest questions in physics. Does this mean one particle is causing the other to collapse? The connection is non-local. It's as if the two particles, however distant, remain part of a single, unified system, sharing a quiet connection across space. So, at the quantum level, we have two gentle problems for causality. First, indeterminism. The same starting conditions do not always lead to the same results. Second, non-locality. Events can be correlated in ways that seem to operate outside the normal rules of space and time. Some frameworks that explore the meeting point of quantum mechanics and gravity even entertain the idea of indefinite causal structures. Imagine a situation where the causal ordering of events itself could be subject to quantum uncertainty. It might not be absolutely true that event A happened before event B. The ground beneath our feet has shifted. In the large-scale world, causality became a statistical pattern born of entropy. In the quantum world, it seems to be absent, replaced by randomness and quiet, non-local connections. The universe, at its most granular level, does not appear to run on a simple principle of cause and effect. It seems to run on principles of possibility and probability. This leaves us with the biggest question. If the foundation of reality is this probabilistic, non-causal place, how do we get our world back? How do we get from this quantum strangeness to the solid, predictable reality of falling cups, ticking clocks, and conscious choices? The answer is one of the most important and quietly beautiful concepts in science: emergence. From parts to a whole, we find ourselves in a curious position. We have looked at the foundations of the universe and found that the bedrock of causality we expected is not there. The fundamental laws are time-symmetric, and the quantum world is governed by probability. And yet, you are here. You made a choice to watch this. That experience feels undeniably causal. So how do we reconcile these two worlds? How does a reliable world of cause and effect arise from a foundation that seems to contain neither? The answer is emergence. Emergence is the observation that complex systems can show properties and behaviors that their individual parts do not have. These new properties emerge from the collective interactions of the parts. A simple example is the wetness of water. If you look at a single H2O molecule, it is not wet. Wetness is not a property of one molecule. It is a quality that arises from the collective behavior of trillions of molecules bonding and flowing together. You cannot understand wetness by studying one molecule by itself. You can only understand it by studying the system as a whole. The same is true for many things. A traffic jam is an emergent property. It is not a property of a single car. It arises from the interactions between many cars. A thought is an emergent property. It is not found in a single neuron but in the synchronized patterns of vast networks of them. Life itself may be the most profound example. A single carbon atom is not alive. But arrange trillions of them in the right way, with other elements, and you can have the astonishing complexity of a living cell. Causality, the argument goes, is like this. It is an emergent phenomenon. It may not exist at the level of individual particles, but it materializes at the macroscopic level, the level of complex systems. How does this happen? Think back to the quantum world, with its randomness. When you are dealing with one or two particles, that randomness is visible. But when you have trillions upon trillions of particles interacting, something remarkable happens. The randomness begins to average out. Out of the quantum chaos, statistical certainties begin to form. The fuzzy probabilities of the micro-world solidify into the sharp, predictable-seeming behaviors of the macro-world. An individual gas molecule in a balloon might be moving in any direction. But the collective pressure of all the molecules is a stable, predictable force. The quantum strangeness of each particle is washed out in the crowd, and a simple, causal relationship emerges. If you increase the temperature, the pressure will increase. This is why classical physics works so well for building bridges. We do not need to know the quantum state of every atom in a steel beam. We can treat the beam as a solid object whose behavior is predictable. The classical laws are an effective theory, a higher-level description that works perfectly at its own scale, even though it rests on a deeper, stranger reality. Causality is our ultimate effective theory. It is the language that complex systems use to describe their behavior. It is a macroscopic story for an incredibly intricate dance of underlying quantum events. When we say, the cue ball caused the 8-ball to move, we are creating a simplified, high-level narrative that is useful for understanding the world at our scale. The deeper story involves an incomprehensible number of quantum interactions. But the emergent story, the causal one, is the one we can perceive and work with. This perspective resolves the question. The laws of physics can be fundamentally non-causal and time-symmetric, while the world we live in is causal and has a clear arrow of time. Both statements are true, they're just describing reality at different levels. There is no contradiction, just as there is no contradiction between a single H2O molecule not being wet and a lake being wet. This view is powerful because it explains why causality feels so real to us. At our scale, it is a real, robust feature of the world. But it also acknowledges that it is not the entire story. It is a description, not a fundamental command. And this brings us to a quiet turning point in our journey. We have seen how the solid ground of causality can dissolve into a quantum fog, and how it seems to reappear at our scale. It's a concept that is both deeply unfamiliar and strangely beautiful. If your mind is turning over the implications of this, that is a wonderful sign. If this kind of calm exploration into the deep nature of reality helps you see the world in a new way, consider subscribing to the channel. This is a place for quiet curiosity, and every video is a slow dive into the ideas that shape our understanding of the cosmos. Your support allows this exploration to continue. If you want more content that quietly challenges your perspective, feel free to join us. Now, we have brought causality back, not as a fundamental law, but as an emergent property of the world we see. But this leads to the most personal question of all. If our brains, our thoughts, and our choices are also emergent phenomena, what does this new understanding of causality mean for us? What does it mean for the feeling that you are in control? The brain's story and the power of choice. We have arrived at the final and most personal part of the puzzle. We have traced causality from a certainty to a statistical pattern, watched it fade in the quantum foam, and seen it re-emerge as a property of complex systems. Now we must turn that lens inward. What about us? What about the feeling of choice that defines so much of our lives? If causality is an emergent, high-level phenomenon, what does that make our choices? The answer may be that a choice is the most sophisticated form of emergent causality we know. Consider the brain. It is perhaps the most complex object we have yet encountered. Billions of neurons, forming trillions of connections. For your mind to navigate the world, it cannot track the quantum state of every particle in your environment. It would be an impossible task. So, the brain does something remarkable. It creates a simplified model of reality. A story. This story hides the impossibly complex code of fundamental physics and presents a clean, intuitive world of objects, people, and, most importantly, causes and effects. The feeling that you chose to pick up a glass of water is the brain's high-level summary of an incredible cascade of neural activity. It is a beautiful and effective summary. You do not need to be aware of the motor neurons firing or the quantum events in your synapses. You just need the conclusion. I decided to get a drink, and now I have. Our consciousness seems to operate entirely at this emergent, causal level. It is a system built to see the world in terms of cause and effect because that is the most effective way to interact with it. This may be why the idea of a non-causal universe feels so alien. We are built to see causes. But this raises a classic, quiet problem. How can a thought, a high-level, emergent pattern, cause an arm to move, which is a physical object governed by low-level physical laws? This is the mystery of downward causation. For a long time, this seemed like a major obstacle. It seemed to suggest that for the mind to have a real effect, it would have to break the fundamental laws of physics, reaching down to meddle with the atoms. But the idea of emergence offers a more elegant solution. Downward causation does not need to violate the low-level laws. Instead, the high-level state of the system can act as a boundary condition for the lower-level parts. Think of a whirlpool in a river. The whirlpool is a high-level, emergent structure. The behavior of any single water molecule inside it is still perfectly governed by the fundamental laws of fluid dynamics. Yet, the whirlpool as a whole, the organized structure, constrains the possible paths the individual molecules can take. It channels their behavior into a collective pattern. The whole shapes the trajectory of the parts without breaking any rules. Our choices could work in a similar way. When you form an intention, that high-level, emergent pattern of neural activity, it doesn't break the laws of physics. Instead, it creates a context that channels the flow of energy through your nervous system in a specific, coordinated way. It constrains the near-infinite possibilities of random neural firings into one coherent, purposeful action. The choice does not create the action from nothing. It organizes the physical processes to achieve a goal. This reframes what a choice is. It is not a magical intervention in the physical world. It is the emergent causal power of a complex system, your brain, to organize its own parts. Your choices are real at the level where you exist. They are the macroscopic patterns that shape the flow of energy and matter in your body. The universe at its fundamental level might not recognize a choice or a purpose. But it has, through evolution, produced systems that do. It has produced brains that have mastered the art of emergent causality. We have become agents of cause and effect in a universe that, at its base, may have neither. This brings us full circle. The feeling of making a choice is not an illusion in the sense that it is fake. It is a real, emergent phenomenon. But the asterisk nature of that feeling, the belief that it is a fundamental act of creating a future from scratch, is a kind of illusion. The reality is more subtle. Your choice is a high-level pattern guiding low-level processes. It is the story the system tells about its own intricate workings. So where does this journey leave us? We started with a simple belief: our choices create the future. We traveled to the bottom of reality and found that the fundamental laws seem to be time-symmetric and non-causal. We saw our familiar world dissolve into a mist of quantum probabilities. It felt, for a moment, as though our choices were being erased by impersonal laws. But then, out of that quiet chaos, we witnessed something remarkable. We saw how complexity can give birth to new kinds of simplicity. How, from the random fizz of the micro-world, the stable patterns of the macro-world emerge. We discovered that causality may not be a fundamental law, but a powerful story that complex systems tell about themselves. The universe doesn't believe in your choices, it is true. But it does something far more astonishing. It builds systems that are capable of believing in them. It evolves brains that operate on the principle of cause and effect, that model the world through the lens of purpose. Our choices are not illusions to be dismissed. They are emergent realities, the achievement of billions of years of evolution. They are the tool with which consciousness navigates its path through the universe. We do not violate the fundamental laws when we choose. We are an expression of what those laws can produce when played out on a canvas of immense complexity. Perhaps the point is not that our feeling of choice is wrong, because it is not fundamental. Perhaps the point is that the emergence of choice, of mind, and of agency in a universe that may have started without them, is the most extraordinary phenomenon of all. We are the universe's way of experiencing a choice. And this opens up one last, quiet question. If causality is an emergent feature of our universe, could other universes exist with entirely different emergent laws? Could there be forms of existence built not on cause and effect, but on principles we cannot yet imagine? The honest and wonderful answer is, we don't know. And the quiet quest to find out is part of what makes us who we are. The math that proves your world is a statistical ghost. Take a moment to look at your hand. It seems solid, doesn't it? Real. You can rest it on a table and feel the unyielding surface of the wood. You can clap your hands together and feel the definite, sharp impact. This sense of solidity is one of the most fundamental truths of our daily experience. It is the boundary that separates the chair you sit on from the air around it. It is what separates you from the rest of the universe. But what if that solidity is not a property of the material itself, but a property of its scale? What if, at a fundamental level, your hand and the chair it rests on are made of almost entirely empty space, populated by a quiet dance of unpredictable particles? These particles do not follow the familiar rules of our world. They are governed by the strange, probabilistic laws of quantum mechanics, where very little is certain, and much is a game of chance. The only reason any of this feels real, the only reason your hand doesn't pass through the desk like a phantom, is because of a quiet mathematical principle. It is a law so profound that it takes the chaos of the micro-universe and from it, builds the stable, predictable reality we inhabit. This is the story of emergence. It is the story of how the simple, elegant law of averages creates our entire world out of quantum uncertainty. It is the story of the math that reveals our world, in a very real sense, is a statistical ghost. And by the end of this journey, you may not look at your own hand in quite the same way again. What if the particles that make up your body are not truly solid on their own, but only become so when billions of them act together? What if the reality we experience, the feeling of the sun on our skin, the taste of food, the sound of music, only exists at a large scale, as a collective agreement reached by trillions of mindless participants? This is not just a philosophical question. It is a central paradox in modern physics. We have two sets of rules for the universe. Down at the level of atoms and electrons, we have quantum mechanics, a world of quiet uncertainty and randomness. In this realm, a particle doesn't have a single, definite location until it is measured. Its properties are described not by solid numbers but by clouds of probability. It is a world of pure, underlying chance. But then there is our world. The world of tables, chairs, planets, and people. Here, things are predictable. If I drop a ball, I know with near perfect certainty where it will land. The laws of classical mechanics are deterministic. They allow us to build bridges that do not collapse and send spacecraft to the outer reaches of the solar system. How can these two realities coexist? How can a universe built on a foundation of randomness give rise to the clockwork predictability we see all around us? The bridge between these two worlds, the principle that transforms chaos into order, is known as statistical mechanics. And it does not just describe the universe. It reveals that the solid world we thought we knew is more of a consensus than a certainty. It is a ghost, born from the mathematics of a crowd. The predictability of crowds. To understand how reality is built from chance, it can be helpful to think about a casino. If you walk into a casino and place a single bet on a roulette wheel, the outcome is almost completely random. You might win, you might lose. The owner of the casino has no idea what the result of that one spin will be. If the casino's entire business depended on individual bets, it would be an enterprise built on pure chance, likely to fail within a week. But, of course, that is not how a casino works. The casino is not concerned with your single bet. It does not care if you win or lose. It cares about the average outcome of millions of bets, placed over thousands of hours. While each individual spin is random, the statistical distribution of those spins is incredibly predictable. The casino knows that over 1 million spins, the ball will land on red a predictable percentage of the time. The house edge is a small, but relentlessly reliable, statistical certainty. The casino's profit is not a gamble, it is a mathematical inevitability. It is an emergent property of a system of countless random events. This is the core principle of statistical mechanics. It is the art of setting aside the chaotic details of individual parts, and instead focusing on the predictable average behavior of the group. Let's leave the casino and consider the air in the room you are in right now. It is filled with an almost unimaginable number of molecules, something like 10 trillion of them. Each individual air molecule is a frantic, chaotic agent, bouncing around at hundreds of meters per second and colliding with other molecules billions of times every second. Trying to track the exact path of even one of these molecules would be an impossible task. It is a microscopic world of pure chaos. And yet, we do not experience this chaos. We experience the stable, predictable properties of the gas as a whole. We experience things like temperature and pressure. But what is temperature? It is not a property of a single molecule. A single molecule of nitrogen does not have a temperature. Temperature is a statistical property. It is the average kinetic energy, roughly, the average speed, of all the molecules in a given area. Similarly, the pressure of the air on your skin is not the impact of one specific molecule. It is the relentless, statistically averaged force of quintillions of molecules battering every square centimeter of your body, every second. These large-scale properties, temperature, pressure, solidity, are the casino's profit. They are the stable, predictable averages that emerge from a system of countless, unpredictable individuals. The universe, it turns out, is the ultimate casino. It uses the law of large numbers to build a stable and predictable world from a foundation of pure chance. Physicists have terms for this: microstates and macrostates. A microstate is a complete description of every single particle in a system, the exact position and momentum of every molecule in the room. This is the realm of chaos, the unknowable, buzzing confusion. A macrostate, on the other hand, is what we actually observe. It is the temperature, the pressure, the volume. It is the big picture view. And here is the crucial insight. There are an unimaginably vast number of different microstates that all correspond to the exact same macrostate. The trillions upon trillions of air molecules can be arranged in a staggering number of different ways, with different positions and speeds, that all produce the exact same temperature and pressure. This is also where the concept of entropy comes from. In statistical mechanics, entropy is simply a measure of how many different microstates can produce a given macrostate. A high entropy state, like gas spread evenly in a room, is a state that can be formed by a huge number of microscopic arrangements. A low entropy state, like all the air molecules suddenly gathering in one corner, corresponds to a vastly smaller number of possible arrangements. The second law of thermodynamics, the rule that entropy tends to increase, is not a fundamental force like gravity. It is a law of probability. The universe doesn't forbid all the air from rushing into one corner. It is just so mind-bogglingly improbable that it would likely never happen in the entire age of the universe. The system simply moves toward the macro state that has the highest number of possible arrangements, the state of highest probability. Order gives way to disorder not because of some cosmic rule, but because disorder is just statistically more likely. So, the solidity of your hand, the steady pressure of the air, the constant temperature of the room, these are not fundamental truths. They are statistical truths. They are the result of our senses taking a blurry, averaged-out poll of an immense population of particles. The solid object is a ghost, an emergent illusion created by the predictability of large numbers. We perceive stability only because we are blind to the chaos of the individuals. The simple rules of creation. So, the stable world is a statistical average. But how does this averaging actually happen? How do trillions of chaotic, individual parts conspire to create the elegant and complex structures we see all around us, from a simple snowflake to a living brain? The answer is that complex, global order can arise spontaneously from incredibly simple, local rules. The universe does not need a grand blueprint or a central conductor to create complexity. It just needs individual agents to follow a few basic instructions, without any awareness of the bigger picture. This is the heart of emergence, complexity arising from simplicity. A perfect illustration of this is the Boyd's algorithm, developed by computer scientist Craig Reynolds in 1986. He wanted to create a realistic simulation of a flock of birds, but realized that programming the behavior of the entire flock at once would be impossibly complex. So, he did the opposite. He did not program the flock at all. He only programmed the Boyds, the individual bird objects, and gave each one just 3 simple rules to follow. The first rule is separation. Steer to avoid crowding your local flockmates. Do not bump into the bird next to you. This is a local, selfish rule. The second rule is alignment. Steer towards the average heading of your local flockmates. Try to go in roughly the same direction as the birds you can see nearby. The third rule is cohesion. Steer to move toward the average position of your local flockmates. Try to stay near the center of the group you see around you. That is all. Notice what these rules do not include. There is no rule that says, form a beautiful, swirling vortex. There is no rule for how to split around a predator and then elegantly recombine. There is no leader, no choreographer, no master plan. Each Boyd is simple. It only knows about its immediate neighbors and follows 3 basic instincts. But when you run the simulation, what you see is breathtaking. From these 3 simple, local rules, a complex, coherent, and stunningly lifelike global behavior emerges. The Boyds swirl and flow as one. They split to avoid obstacles and then seamlessly merge back together. They form a collective entity, the flock, that has properties and behaviors that are not present in any individual Boyd. The flock is a statistical ghost. It is an emergent phenomenon. It does not exist in any single Boyd, it exists only in the interactions between them. You cannot find the flock by looking at a single bird. The flock is what the system does, not what its parts are. This principle of simple rules leading to complex systems is everywhere. Consider another well-known example, John Conway's Game of Life. This is a simulation, or a zero-player game. You start with a grid of cells, each either alive or dead, and let it run according to 4 simple rules. 1. A living cell with fewer than 2 living neighbors dies. 2. A living cell with more than 3 living neighbors dies. 3. A living cell with 2 or 3 living neighbors lives on. 4. A dead cell with exactly 3 living neighbors becomes a living cell. Again, these are profoundly simple, local rules. A cell only cares about its 8 immediate neighbors. But the results are anything but simple. From these rules, you get an entire emergent zoo of creatures. Some are static patterns, others oscillate, and famously, you get gliders, patterns that move across the grid like tiny, quiet spaceships. People have even built fantastically complex machines within the game of life, showing that a system based on simple rules can perform incredibly complex tasks. These are computer simulations, but the same principle governs the physical world in the form of phase transitions. A phase transition is what happens when a substance changes its state, like water turning into ice. Think about the individual H2O molecules in liquid water. They are jumbled, disordered, and can move past one another, a disorganized crowd. As you lower the temperature, you are simply reducing the average energy of these molecules. At a certain point, 0 degrees Celsius, a threshold is crossed. Suddenly, the simple, local rule of attraction between molecules overwhelms their chaotic, individual motion. The molecules snap into a highly ordered, crystalline lattice. The disorganized crowd becomes a disciplined army. The result is ice. Ice has properties that liquid water does not. It is hard, brittle, and less dense. These properties of iciness are not found in a single H2O molecule. They are emergent properties of the collective structure. The transition from liquid to solid is an emergent phenomenon, a spontaneous leap into a new level of organization, driven by a simple change in a background condition. This is the mathematical principle in action. From the simple, local rules governing particles, to the complex, global behaviors of matter, the story is the same. The flock, the glider, the ice crystal. They are all statistical ghosts, predictable patterns conjured into existence by the law of averages working on a crowd of mindless individuals. The world we see is not a world of things, but a world of patterns. And those patterns are written in the language of mathematics. The ghost and the machine. We have seen how the solid, predictable world emerges from the math of large numbers, and how complex structures can be built from simple, local rules. The flock of birds is a pattern. The hardness of ice is a pattern. The pressure of a gas is a pattern. Now we can turn to a quieter, more profound question. What if we are a pattern, too? This journey from the micro to the macro, from chaos to order, is not just about inanimate matter. It is the story of life itself. And perhaps the most profound example of emergence is sitting right between your ears. Your own consciousness. There is no single neuron in your brain that is conscious. There is no awareness molecule or thought atom. A single neuron is a biological machine. It follows a set of simple, local rules. It receives electrochemical signals from its neighbors. If those signals cross a certain threshold, the neuron fires, sending its own signal to other neurons. It is a simple input-output device. It is a void. It is a cell in the game of life. But from the impossibly complex network of 86 billion of these simple neurons, each following its local rules, each communicating with thousands of its neighbors, something entirely new emerges. A property that none of the individual parts possess: self-awareness. Your thoughts, your feelings, your memories, your sense of self. It all arises from the collective dynamics of this neural flock. Consciousness is a statistical ghost. It is a ghost in the machine. You cannot find you by dissecting the brain. You will only find neurons, glial cells, and chemical signals. The you that is listening to these words right now is an emergent pattern, a global behavior of a complex system. Just as the flock's behavior is more than the sum of its birds, your mind is more than the sum of its neurons. This parallel is so powerful that it has led scientists to look for a deeper, more universal principle at play. The simple rules model is a powerful explanation, but what if those rules are an expression of something even more fundamental? A framework in theoretical neuroscience called *active inference*, pioneered by Carl Friston, suggests that the driving force behind this collective behavior might be a single, elegant imperative: to minimize surprise. This idea proposes that any self-organizing system, from a single cell to a human brain, builds a model of its world, and then it acts to make reality match its model's predictions. In other words, it works to minimize prediction error, which is just a mathematical way of saying it tries to avoid being surprised. Let's return to the flock of birds. The old model says a bird follows 3 rules: align, cohere, separate. The active inference model suggests something deeper. It says that each bird has an internal model of what it expects to experience as a member of a flock. It expects to see other birds around it, moving in roughly the same direction. If a bird finds itself suddenly alone, or sees its neighbors veering off sharply, that creates a prediction error. It is a surprise. To resolve this surprise, the bird acts. It changes its own course to get back into the group, to make its sensory input match its quiet expectations again. Under this view, the rules of cohesion and alignment are not programmed in. They emerge as the natural consequence of each bird trying to minimize its own local surprise. The elegant dance of the flock is the collective solution to a million individual prediction problems. Coordinated movement is what happens when a group of agents all share the same basic expectations about their world and work to fulfill them. This is a profound shift in thinking. It reframes behavior not as a response to the world, but as an action taken to confirm an internal model. Organisms are not passive objects being knocked around by the environment. They are active, inference-making machines, constantly trying to impose their predictions onto the sensory chaos they're bathed in. And this brings us to the quiet, philosophical payoff. If active inference describes the behavior of neurons, and also the behavior of flocks, what does that imply? It implies that the same fundamental process, the minimization of surprise through action, may be responsible for creating emergent order at every scale of reality. It bridges the gap between the physical and the mental. The flock behaves as if it has a mind of its own. But that mind is an illusion, emerging from the simple, surprise-minimizing actions of its members. Our own mind behaves as if it is a single, unified thing. But it too may be an emergent property, arising from the surprise-minimizing actions of billions of individual neurons, each with its own tiny, predictive model of its local world. This framework suggests that a form of cognition, a kind of predictive intelligence, is not something that magically appears at the level of a whole brain. It is happening all the way down. The tendency to build models and act to confirm them might be a fundamental property of self-organizing matter. This does not mean a neuron is conscious, but it does mean that the building blocks of consciousness might be far more fundamental and widespread than we ever imagined. The world is not just a statistical ghost. It is a predictive machine. It is a constant conversation between internal models and external reality, a dance of expectation and action that plays out from the scale of a single cell to the scale of an entire society. The ghost, it seems, is actively trying to haunt itself into existence. So, let us return to where we began. Your hand. It still feels solid. The desk it rests on still feels real. But our journey has shown us that this solidity is a beautiful, persistent, and profoundly useful pattern. We started by questioning the nature of this solidity, framing it as a quiet paradox between the uncertain quantum world and our predictable classical world. We found that the bridge between them is the mathematics of statistics. The solid world we perceive is a macrostate, a blurry, averaged-out consensus of an unfathomable number of chaotic, microstates. The certainty of our world is built on the law of large numbers, just like the profits of a casino. We then explored how this statistical principle creates structure. Through the elegant example of flocking birds and cellular automata, we saw how simple, local rules can give rise to sophisticated, global, emergent behavior. The flock is not in the bird, it is in the interaction. The hardness of ice is not in the water molecule, it is in the collective crystal. The whole becomes something else entirely, a new level of reality. Finally, we turned this lens inward. We saw that our own minds are perhaps the ultimate emergent phenomenon, a ghost in the biological machine, arising from the simple, rule-following actions of billions of neurons. And we touched on the frontier of this science, the idea that all emergent order might be driven by a single, deeper principle: the minimization of surprise. So, is your world a ghost? An illusion? The answer is a subtle one. The solidity, the stability, the very thingness of the objects around you is an illusion, in the sense that these properties do not exist at the most fundamental level of reality. They are not properties of the individual particles that make them up. But they are, without question, real. They are real emergent properties. The flock is real to the hawk that hunts it. The hardness of ice is real to the ship that it sinks. Your consciousness is real to you. Emergence does not make the world less real. It reveals that reality exists on multiple levels at once. The chaotic dance of the quantum particle is real. The statistically certain behavior of the collective is also real. They are just different descriptions of the same universe, one seen with a microscope, the other with our own eyes. The universe is not a single story. It is a library of stories, each told at a different scale. And the great secret is that they are all consistent with one another. The math of statistics and emergence is the language that translates the story of the parts into the story of the whole. The next time you look at your hand, you are not just seeing a physical object. You are witnessing a cooperative agreement on a scale you can barely comprehend. You are seeing a statistical ghost, a pattern of unimaginable complexity, conjured for a fleeting moment in cosmic time by the unfathomable dance of countless chaotic particles, all held together by the simple, elegant, and inescapable power of the law of averages. It is perhaps the greatest quiet magic trick in the universe. And you are a part of it. If this quiet exploration into the statistical heart of reality helped you unwind, and you enjoy entangling the deep questions about our universe and our place in it, consider subscribing and joining our journey into the biggest ideas in science. The rabbit hole goes much deeper. You are not solid, your body is a statistical blur. You feel the weight of your body, the warmth of a cup in your hand, the undeniable presence of your own existence. It feels real, solid, permanent, and for most of human history, this was the only truth we knew. But science, in its quiet quest to understand reality, has revealed a profoundly different picture. What if that feeling of solidity is an illusion? What if the you that feels so constant is not a single entity, but the most likely outcome in a storm of quantum probabilities? This is a journey into that idea. Not to dismantle your sense of self, but to rebuild it with the strange and profound truths of quantum mechanics. By the end, you may not see yourself, or the world, in quite the same way again. If this kind of calm exploration into the nature of reality helps you think, consider liking the video and subscribing to the channel. And wherever you are right now, feel free to share your thoughts in the comments below. The grand illusion of solidity. Let's begin with something simple. Look at your hand. It seems to be the most real thing in the world. You can clench it into a fist. You can feel the texture of your skin. It stops light and can knock on a table to produce a solid sound. This is our everyday experience, the foundation of our reality. The first crack in that foundation comes from a simple, yet startling fact. Your hand, your body, the chair you're sitting on, are all 99.9999999% empty space. If you were to take all the actual matter from every one of the 8 billion people on Earth and compress it, removing all that empty space, the entire human race would fit into the volume of a single sugar cube. Think about that for a moment. Everything you perceive as solid is almost entirely nothingness. What gives it the illusion of substance lies in its building blocks, atoms. You are made of an almost unimaginable number of them. trillions upon trillions of atoms that make up the whole of you. We learn in school that an atom is like a tiny solar system, with a dense nucleus and electrons orbiting like planets. This image, while helpful, is also misleading. Those electrons are not tiny, solid balls in neat circles. They are better described as probability clouds. An electron does not exist at any single point. Instead, it exists in a state of superposition, a ghostly haze of all its possible locations at once. The cloud represents the statistical likelihood of finding the electron if you were to look for it. It is a statistical blur. The solidity you feel when you clap your hands is not the contact of two solid objects. It is the electromagnetic repulsion between the electron clouds of the atoms in one hand and the atoms in the other. You have never truly touched anything in your life. You have only ever felt the force field of its statistical boundary pushing against yours. But the illusion runs deeper. Not only is the material you are made of mostly empty space, but that material is constantly being replaced. There's a popular idea that the body replaces itself every 7 years. The truth is more complex, and far more interesting. The cells lining your stomach may last only 5 days. Your red blood cells are replaced every 4 months. Your skin is constantly regenerating. Other cells, like those in your bones, take a decade or more to be fully replaced. And some of the most important cells, like most neurons in your cerebral cortex, are with you for life. They are rarely, if ever, replaced. You are a mosaic of materials with different turnover rates. A system in constant flux. The physical particles that constitute your being are transient, flowing through you like water through a riverbed. If you are not your atoms, which are always changing and are not solid to begin with, then what, exactly, are you? To answer that, we have to go deeper, to a foundational experiment that revealed the probabilistic nature of existence itself. The double-slit experiment, reality's foundational glitch. To understand what you are, we first need to understand what is. For the last century, our most profound tool for this has been a deceptively simple setup, the double-slit experiment. The physicist Richard Feynman described it as containing the central mystery of quantum mechanics. It reveals a world that, at its most fundamental level, does not behave in ways that feel familiar or intuitive. Imagine a barrier with 2 narrow slits in it. On one side, a machine fires objects. On the other, a screen records where they land. First, we fire something familiar, like paintballs, one at a time. Some are blocked, some go through the left slit, some through the right. On the screen, we see 2 distinct bands of paint behind the slits. This is what you would expect. It is particle behavior. Now, let's use waves in a tank of water. As the waves pass through the 2 slits, they spread out and interfere with each other. Where 2 crests meet, they create a bigger wave. Where a crest meets a trough, they cancel out. The screen shows an interference pattern, many bands, not just 2. This is wave behavior. Now, for the main event. We fire electrons, the components of atoms, one at a time. An electron is a particle. It has mass and charge. So, we should expect to see 2 bands, just like the paintballs. We turn on the machine. The first electron lands, making a single dot on the screen. Then another, and another. We leave the experiment running for hours. As the pattern emerges, a sense of profound unfamiliarity appears. The pattern is not 2 bands. It is an interference pattern. This result seems impossible. The interference pattern is the signature of waves interfering with each other. But we fired the electrons one by one. The only thing each electron could have interfered with is itself. This implies that each electron, upon reaching the barrier, became a wave of possibility. It did not go through the left slit or the right slit. It went through both slits simultaneously, its potential paths interfering with each other. The particle only appears at a definite location when it hits the screen. Before that, it is pure potential. This is where the mind pushes back. It must have gone through one or the other, we just didn't know which. So, we decide to look. We place a tiny detector at the slits that tells us, for each electron, whether it went through the left or the right. We rerun the experiment. The first electron is fired. Our detector flashes. Left slit. A dot appears on the screen. The next, right slit. Another dot. We let it run. We have our data. We know the path of every electron. But when we look at the final pattern on the screen, the feeling of strangeness returns. The interference pattern is gone. In its place are two distinct bands, just like the paintballs. The very act of observing which path the electron took forced it to behave like a particle. The moment we gained knowledge of its path, its wave of possibilities collapsed. It is important to understand what observation means here. It has nothing to do with human consciousness or mystical forces. In quantum mechanics, an observation is any physical interaction that extracts information from a system. The detector at the slit has to interact with the electron to determine its position. That interaction, that physical jostling, is the measurement. It is the act of the universe, finding out where the electron is. That interaction forces the blur of probability to resolve into a single, concrete fact. This is the fundamental rule of the quantum world. Before a measurement, a particle exists as a wave of all possibilities. After a measurement, it is forced into a single, definite state. Reality at its base is not a collection of things, but a collection of probabilities. And this rule governs every atom in your body. From one particle to trillions, the secret of being solid. This leaves us with the largest question. If the building blocks of reality are ghostly waves of probability, why isn't the world a shimmering, uncertain haze? Why does a table feel solid? Why do you remain a distinct person, instead of dissolving into a cloud of potential when left unobserved? The answer is a concept in modern physics called quantum decoherence. It is the bridge between the strange quantum realm and our solid, everyday reality. Let's return to our single electron, protected in the vacuum of a laboratory. There, we can shield its delicate superposition, allowing it to be a wave. Its quantum secret, that it is in multiple states at once, is safe. But imagine a single, stray air molecule bumps into that electron. That interaction is a measurement. The air molecule has now found out where the electron is. The electron's superposition instantly collapses. It is forced to be in one place. But it gets deeper. By interacting, the air molecule and the electron have become entangled. The quantum secret is now shared. The air molecule then immediately bumps into another, and another. The information about the electron's original state leaks out into the surrounding environment at an almost incomprehensible speed. Think of it like a drop of ink falling into an ocean. In an instant, the concentrated drop is gone, its information hopelessly dispersed among trillions of water molecules. This rapid leakage of quantum information into the environment is decoherence. The environment is constantly performing measurements. Now, think about your body. You are not a single electron in a vacuum. You are a warm, complex system of trillions upon trillions of atoms. You are being bombarded by photons from the light in your room. You are being pelted by quintillions of air molecules. Your own body heat causes your atoms to vibrate and jostle against each other constantly. Each of these interactions, a photon bouncing off your skin, an air molecule hitting your arm, is a tiny measurement. Each measurement asks a quantum particle, "Where are you?" and collapses a superposition. This is happening at a rate so fast and across so many particles that it is essentially continuous. This is why you are solid. Solidity is not a fundamental property of matter. It is an emergent illusion created by the universe's constant, relentless act of self-measurement. Your body appears solid because the overwhelming statistical probability, enforced by constant environmental decoherence, pins it down into a single, stable reality. You are not allowed to be a ghostly wave, because the environment is constantly interacting with you, forcing you to be here. The sheer number of these interactions creates a consensus reality for any large object. The you that feels solid is a statistical certainty, the result of quantum probabilities being averaged out over an immense number of particles. You are a blur of quantum potential that has been sharpened into focus by the relentless observation of the world around you. Section 4. The statistical self. Who are you? We have arrived at the heart of the matter. Your physical body is mostly empty space, made of particles that are waves of probability, held in a solid-seeming form by constant environmental interaction. So what is the self? What is this continuous stream of consciousness that inhabits this probabilistic machine? Let's revisit the fact that your material composition is in constant flux. The atoms that make up your hand today are not the same atoms that made it up a few years ago. If your identity were tied to your specific matter, you would be a different person every day. The quantum perspective reveals an even deeper truth. At the fundamental level, particles like electrons do not have unique identities. If you have two electrons, you cannot label one A and the other B and track them over time. They are fundamentally indistinguishable. The very concept of the same electron loses its meaning. If the particles that make you up are constantly being replaced, and those particles have no individual identities to begin with, what is it that persists? What is the thread that you identify as you? The answer is as profound as it is simple. You are not the matter. You are the pattern, asterisk. You are not the particles, but the incredibly complex and dynamic arrangement of those particles. You are the information encoded in that structure. You are a process, not a thing. Think of a whirlpool in a river. It has a distinct shape, a location, and properties. But the water molecules that constitute the whirlpool are always changing. Water flows in, swirls, and flows out. The whirlpool is not the water. It is the dynamic, self-sustaining pattern the water is following. The pattern persists, even as the substance changes. You are that whirlpool, a vastly more complex and self-aware one, but a pattern nonetheless. Your memories are not stored in specific atoms, but in the structural connections between neurons. Your personality is an emergent behavioral pattern of your neural network. Your consciousness is the activity of the pattern itself. This is what it means to be a statistical blur. At any moment, there is a probability cloud for where every particle in your body could be. Your solid form is simply the overwhelmingly most probable configuration of that vast cloud. There is a vanishingly small, but non-zero, quantum probability that all the atoms in your body could suddenly tunnel through the floor. It is so unlikely that you would have to wait trillions of times the age of the universe for it to happen, but according to physics, it is not impossible. Your feeling of being a single, continuous self is the experience of this pattern maintaining its integrity over time. It is your biological systems, guided by the information in your DNA, working to maintain the pattern. You are not a static object. You are a process. And this realization does not diminish you. It means your existence is not tied to any piece of matter, but to the sublime, intricate dance of information and energy that creates and sustains your form. The edge of knowledge, consciousness, and the great mystery. We have now traveled from the tangible world to the edge of established physics. It is important to state that we are moving into more speculative territory, where hard answers give way to profound questions. We have described the physical body as a stabilized pattern. But what about the mind that perceives it? From the perspective of mainstream neuroscience, consciousness is seen as an emergent property. It is the holistic, system-level behavior that arises from the staggering complexity of the 100 billion neurons in your brain. It is what happens when the whirlpool becomes complex enough to be aware of itself. However, the persistent strangeness of quantum mechanics has led some physicists and philosophers to wonder if there is a deeper connection. They argue that the mystery of quantum measurement and the mystery of consciousness might be related. It must be stressed that these ideas are highly controversial and are not part of the mainstream scientific consensus. They represent the frontier. This territory is mapped by thought experiments like Wigner's friend. Imagine a physicist, a friend, inside a sealed lab. She performs a quantum measurement, collapsing a particle's superposition into a definite state. For her, reality is now definite. But for her colleague, Eugene Wigner, outside the lab, the story is different. From his perspective, the entire lab, his friend, her device, and the particle, can be seen as one large quantum system. For Wigner, this whole system is in a giant superposition until he opens the door and interacts with it. So when did reality become definite? When the friend measured it? Or only when Wigner observed his friend? This probes the very definition of measurement and asks where the line is drawn. Does consciousness cause collapse? Or is consciousness simply what it feels like when a collapse happens inside a complex brain? Does reality branch into multiple worlds with each measurement? The honest answer is, we don't know. Physicists still debate the correct interpretation of quantum mechanics. And that uncertainty is not a failure, it is the most exciting part. It tells us we are still in the process of discovery, still peeling back the layers of a universe that is far stranger and more interconnected than we ever imagined. We began this journey with the solid, common sense you. We saw that this self is mostly empty space, populated by ghostly particles that exist in a blur of probability. We saw how the double-slit experiment proves that existence is probabilistic until a measurement forces its hand. And we saw how quantum decoherence, the universe's constant act of self-observation, forges our solid world from that quantum fuzz. The final revelation is this: you are not a thing. You are a pattern, a dynamic, self-sustaining process. The you that you experience is a statistical likelihood, a temporary, beautiful, and astonishingly complex arrangement in a universe of endless, shimmering potential. Look at your hand again. It still looks solid. It still feels real. But now you know the truth. You are not looking at an object. You are looking at an event. A statistical certainty, happening right now. The real question is, what event happens next? The universe is pretending to be solid. The world feels solid. The ground beneath our feet, a chair, the phone in our hands. These things feel stable, dependable, real. This sense of solidity is perhaps the most fundamental part of our experience, the baseline against which we measure everything else. And yet, it is an idea built on a foundation that is almost entirely empty. The feeling of a solid object is, in a quiet but profound sense, an illusion. It is a sensory story our world tells us. The atoms that make up your body and the atoms that make up the chair you are sitting on are not truly touching. What you perceive as unyielding resistance is the echo of invisible forces and quantum rules, creating a stable world from a foundation of shimmering uncertainty. The question, then, is what holds this world together? If you are not solid, and the chair is not solid, what is actually preventing you from passing through the floor? The answer is a journey to the edge of our perception, to a place where familiar rules are replaced by laws so unfamiliar they seem to belong to another reality. This is the story of how the universe builds the concrete, predictable world we see from a place of pure and uncertain potential. For a long time, the explanation for solidity seemed simple. It was an idea that formed the bedrock of physics for centuries, that matter, at its most fundamental level, is made of tiny, indestructible, solid balls. Like microscopic marbles. The ancient Greeks called them atoms, meaning uncuttable. It was a picture that made intuitive sense. It explained why a rock was hard and why a person could not walk through a wall. The tiny marbles of the wall were simply in the way of the tiny marbles that made up the person. This was the world of classical physics, a predictable, tangible, and solid reality. If one knew the position and momentum of every particle, one could, in principle, know the entire future of the cosmos. It was a comforting thought. But this simple view of the world was about to be challenged by an experiment that would look into the heart of the atom and find almost nothing at all. The year is 1909. In a laboratory in Manchester, England, the physicist Ernest Rutherford, along with his colleagues Hans Geiger and Ernest Marsden, devised an experiment to probe the structure of the atom. The dominant model at the time was the plum pudding model, which imagined the atom as a diffuse sphere of positive charge with negative electrons scattered within it. It was pictured as a soft, somewhat uniform ball. Rutherford's experiment involved firing tiny, positively charged alpha particles at a sheet of gold foil only a few atoms thick. Around the foil, a screen was placed that would flash whenever it was struck by an alpha particle. The expectation was straightforward. If atoms were soft, the fast-moving alpha particles should pass directly through them, perhaps deflecting slightly. For days, Geiger and Marsden sat in the darkened lab and counted the flashes of light. And for the most part, the results were as predicted. The vast majority of particles went straight through the foil. But then, they observed something entirely unexpected. Roughly 1 in every 8,000 particles did not go through. Instead, it bounced back, sometimes at a large angle. Rutherford would later describe his astonishment with a now famous analogy. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. The soft plum pudding model could not explain this. The only explanation was that the atom was not a uniform ball. Instead, almost all of its mass and all of its positive charge had to be concentrated in an incredibly small, dense center, a nucleus. This discovery gave birth to the nuclear model of the atom, revealing a structure that is difficult to truly comprehend. The atom was not a solid marble, it was more like a miniature solar system, with a central nucleus and orbiting electrons. The scale of this system was the most mind-bending part. To visualize it, if the nucleus were a single marble in the center of a vast football stadium, the electrons would be like grains of sand moving through the outermost seats. Everything else, the entire volume of that stadium, would be, for all intents and purposes, empty space. In fact, an atom is understood to be about 99.9999999% empty space. This presents a paradox. If the atom is mostly empty space, and everything is made of atoms, then our world is fundamentally empty. The question becomes urgent. If I am made of empty space and my chair is made of empty space, why does my hand not pass right through it? Why do things feel solid? The classical idea of solidity was gone. The answer had to lie in the new, strange rules that governed this empty, atomic world. The reason you do not fall through the floor is not because of solid surfaces making contact. The sensation of touch is an illusion created by a force. When you press your hand against a desk, the atoms in your hand never get close to the atoms in the desk. What you feel is the electromagnetic force. The empty space of an atom is the domain of electrons. But with the discovery of quantum mechanics, it became clear that electrons are not like tiny planets. An electron does not exist at a single point, but as a probability cloud, a region of space where it might be found. This cloud is the manifestation of its wave function. These electron clouds are negatively charged, and like charges repel. As the atoms of your hand approach the atoms of the desk, their outer electron clouds get closer, and the repulsive force between them grows stronger. This electromagnetic repulsion is what we perceive as touch and solidity. You are not touching the desk. You're feeling the force field of its electrons pushing back against the force field of your own. But this is not the full story. Electromagnetism explains the repulsive force, but not why matter itself doesn't simply collapse under pressure. This deeper answer comes from a principle discovered by the physicist Wolfgang Pauli in 1925. It is called the Pauli exclusion principle, and it is the ultimate source of structure in the universe. In simple terms, the Pauli exclusion principle states that no two identical fermions, a class of particles that includes electrons, can occupy the same quantum state at the same time. A quantum state is like a unique address for a particle, defined by properties like its energy and spin. Think of it as an auditorium with strict seating rules. Each seat is a unique quantum state. The Pauli exclusion principle is the rule that only one electron can occupy each seat. This gives atoms their structure and volume. As electrons are added to an atom, they are forced into higher and higher energy levels, creating the distinct electron shells that define every element. Without this principle, all electrons would collapse into the lowest energy state, and there would be no structure, no chemistry, and no volume. When you press your hand against a desk, you're trying to force the electrons in your hand to occupy the same quantum states as the electrons in the desk. The Pauli exclusion principle forbids this. This refusal manifests as an immense repulsive pressure, a purely quantum effect that has nothing to do with charge. It is a consequence of the law that no two things can be in the same state in the same place. The feeling of solidity is a two-part phenomenon. First, the electromagnetic repulsion between electron clouds. But the unyielding nature of that solidity is the Pauli exclusion principle. It is a quiet, collective declaration that this space is already occupied. This reveals a deeper problem. According to classical physics, Rutherford's atom should be unstable. A charged electron orbiting a nucleus should radiate energy, causing it to spiral inward and crash into the nucleus in a fraction of a second. Every atom in the universe should have collapsed long ago. Clearly, they have not. So, what invisible law prevents this? The answer is one of the most fundamental principles in science, introduced by Werner Heisenberg in 1927, the Heisenberg uncertainty principle. It states there is a fundamental limit to how precisely certain pairs of properties, like position and momentum, can be known at the same time. This is not a limit of our tools, it is an inherent fuzziness in reality itself. A particle simply does not have a perfectly defined position and a perfectly defined momentum simultaneously. This uncertainty is what saves the atom from collapse. As an electron gets closer to the nucleus, its position becomes more confined. According to the uncertainty principle, as the uncertainty in its position decreases, the uncertainty in its momentum must increase. This would give the electron so much kinetic energy that it would overcome the nucleus's attraction. The electron is pulled in by charge but pushed out by uncertainty. The result is a stable equilibrium, a ground state where the electron settles without ever falling into the nucleus. The very principle that introduces a fundamental randomness into the universe is what guarantees its stability. It creates a kind of quantum pressure that inflates the atom and gives it its size. This brings us to the role of observation. In the double-slit experiment, a particle like an electron can act as a wave, passing through two slits at once. But the moment a detector is used to see which slit it goes through, the wave behavior vanishes, and it acts like a particle. The act of measurement seems to force the particle to abandon its state of multiple possibilities and collapse into a single, definite reality. Reality at this level is not a fixed thing, but a shimmering sea of probabilities that only solidifies when it interacts with something else. This leads to a final, crucial question. If the quantum world is so strange, why does our world appear so normal? Why doesn't a chair exist in a superposition of being in multiple places at once until we look at it? The bridge between these two worlds is a process known as quantum decoherence. An isolated quantum particle can exist in a superposition of many states. But in the real world, nothing is truly isolated. The environment is a chaotic place, and that single particle is constantly being bombarded by photons, air molecules, and thermal vibrations. Each tiny interaction is like a miniature measurement, leaking information about the particle's state into the environment. As the particle becomes entangled with more and more of its surroundings, its delicate quantum state is spread so thin that it effectively disappears. For a macroscopic object like a chair, the number of interactions with its environment is astronomically large, and this process happens at an astonishing speed. Any quantum superposition is almost instantly destroyed, forcing the object to choose a single classical state. It is not that quantum laws stop applying, it is that their effects are averaged out over an unimaginable number of interactions. This is the birth of the classical world. It emerges from the quantum substrate as a consequence of massive statistical averaging. The solidity of your chair is an emergent property. An individual atom does not have a property called solidity. But when trillions are arranged together, held apart by forces and principles, and locked into place by decoherence, the system as a whole exhibits the property we call solid. The classical world is not fundamental. It is a high-level phenomenon born from the relentless, statistical noise of the quantum realm. We live at a scale where decoherence has washed away all the overt strangeness, leaving behind a stable, predictable, and reassuringly solid-feeling reality. The chaos is still there, humming just beneath the surface. If this quiet exploration into the nature of reality is something you find valuable, consider subscribing to the channel. And feel free to share your thoughts in the comments. How does this change the way you see the world around you? We began with the simple sensation of a solid object. We end with the understanding that solidity is an emergent property, a stable pattern arising from an underlying reality of pure potential. The atoms in that chair are mostly empty space, held in shape by the phantom of electromagnetic force. Their structure is maintained by the uncertainty principle, and their volume is a consequence of the Pauli exclusion principle, a cosmic rule that forbids them from occupying the same state. The reason this all appears as a single, unwavering object is due to quantum decoherence, the constant, noisy interaction with the environment that forces it to pick a state and stick to it. The classical world emerges from the quantum world not by erasing the weirdness, but by averaging it into oblivion. The great irony is that the stable world we depend on is only possible because its foundation is uncertain. Order emerges from randomness. Solidity is born from emptiness. What we perceive as reality is a macroscopic story, told on such a massive scale that we cannot see the individual, contradictory words it is written with. This leaves us with a quiet thought. If the feeling of solid is a kind of high-level perception, what other aspects of our reality are the same? The universe is not just pretending to be solid. It is reminding us that what we perceive is only one layer of a much deeper and far stranger story.